Hi, Matt. Hi, can you hear me?
Hi, Matthew. Hi, Matthew and Matthew.
Hi, Matt. I'm going to apologize. I'm going to have to leave early. So,
No.
Oshi, can you hear Matthew?
I can hear.
Moshi, can you hear me?
Yeah, how are you doing?
A little crazy, but I'm doing okay. I'm going to have to leave early again today.
Which side of the continent are you?
I'm in LA until I get immunized.
Fair enough. Matthew, haven't seen you in a long time.
I know.
Oh, Matthew. Yeah, how you doing, Matthew?
Hi, how you doing?
You just like to go to meetups that are led by other people named Matthew.
Even those meetings, haven't seen this Matthew too often.
I think Matt Weiss cut out on us. He can't take the pressure. Let's see him. Oh, there he is.
I
Matt,
was
is this,
hoping you would leave, Mike.
Matt, is
you
this
hear
the psychedelic LSD meetup? Matt, is this the psychedelic LSD?
I can hear you now.
Okay.
Okay, sorry, I had these AirPods, and okay, anyway, been a day of Zoom troubles.
Can I
How's
ask you
everyone
a
doing?
question before we start?
Yeah, sure.
Oliver Wendell Holmes Jr., was he the Supreme Court Justice or the son of the Supreme Court Justice?
That's a good question. I thought he was, but maybe not.
This Supreme Court Justice
Yeah,
who believed in
junior and senior.
euthanasia and phrenology and all that stuff. Where did he study physics?
Yeah, Junior was the associate justice of the Supreme Court.
And he was quoted by the Nazis in justifying their euthanasia and
Ouch,
phrenology
burn. Okay,
and all the other stuff they did. But where did he study physics?
I don't think he was a physicist.
Oh, okay, because you're quoting him.
Yeah, that's true. You know, sometimes you can quote people who aren't physicists.
Not here, you can't.
All right.
Who are you talking about?
Oliver Wendell Holmes Jr. You know, just to give a sense. So, okay, like, I mean, one of the things that, you know, if you read the Cubists, you know, who include people like Christopher Fuchs and Blake Stacy and this guy Shack and others, they are just like sort of interested in the history of like American pragmatism. So people like Charles Sanders Peirce from the 19th century, William James, John Dewey, and you know, Oliver Wendell Holmes Jr. I guess was somewhat associated later on.
Who also quoted Oliver Wendell Holmes?
Who?
The defense attorneys at the Nuremberg trials. If anybody saw the movie Judgment at Nuremberg, where Maximilian Schell played the defense attorney for the Nazis who were on trial, he kept quoting Oliver Wendell Holmes as legal justification for what the Nazis did.
In what on what grounds?
On what grounds?
It was a
I told you,
pragmatic
Oliver
thing to
Wendell
do.
Holmes believed in sterilization of inferior people, you know, and
Well,
shit
we
like
have no
that
trust
that
with
we
that.
don't
Mike,
approve
Mike,
of
you
anymore.
better be careful. If you go on, Matt is going to sterilize you.
Well, you know, I'm not already sterilized. My ex-wife may have done that. I don't know.
Oh, lol. Okay, all right.
Not
So
allowed to
let
talk
us
philosophy. No more philosophy. Let's just see an
no
equation.
more philosophy. Okay, okay. Yeah, well, you know, we have it organized. I do the math first, so you'll be pleased. So, all right, sharing the screen. Participants. All right, just making sure my windows are all set up here. Okay, yeah, so, yeah, as I say, you know, Qbism is yet another interpretation of quantum mechanics. You know, there's always more. And like any good interpretation, there's, you know, a kind of mathematical component, and there's a philosophical component. And, you know, in some ways they're kind of separable from each other. And so, you know, you look at the papers they put out, you know, as part of this research program, and certainly, you know, whether you sign on to their, you know, whole philosophical thing, they have some really interesting points, you know, about the math of quantum theory. And in particular, its, you know, relationship to normal probability theory. And so we'll sort of get a sense of that formalism at the outset here. So, you know, textbook quantum mechanics says that, you know, okay, you want to make a measurement. You got a observable. It's represented mathematically by a Hermitian operator. And we're going to call this like a von Neumann measurement to distinguish it from a more generalized notion of measurement that we're going to come to. So a von Neumann measurement consists of a choice of observable represented by a Hermitian operator. Such an operator will have real eigenvalues and orthogonal eigenvectors. For example, H could be the energy operator, and then, you know, eigenvectors would represent possible energy states, and eigenvalues would represent possible values of the energy. And again, according to textbook quantum mechanics, you know, whatever, just looking at the axioms or whatever, they say the system ends up after a measurement in a state that will in general be random, and quantum mechanics allows you to calculate the probabilities. So a Hermitian observable provides what's known as a projection valued measure. So suppose our system state, you know, was represented by some density matrix rho, you know, in all generality. We could form a set of projectors, which are just the outer product of the different eigenvectors with themselves. And then the probability for, you know, the ith outcome will be given by just this trace. Multiply the projector by the density matrix, take the trace, you get your probability. And the state after measurement will basically be, you know, given by the actual projection. You kind of wedge rho in there. The expectation value of an observable H will be given by the trace of H on rho. And, you know, it amounts to a sum over the eigenvalues weighted by the corresponding probabilities. So, you know, just to remind you all how this works, you know, let's choose a dimension, say 2. We can construct a random, you know, density matrix, a random Hermitian matrix, find its eigenvalues and eigenvectors. We can form these projectors, and then we can take the trace of the projector on rho on each of the projectors, and then we can look at, okay, here's the probabilities. The expectation value is just H on rho, take the trace. And that's exactly the same thing as taking those probabilities and allowing them to weight the different eigenvalues and taking a sum. And oh, look at that, 0, nice. Get the same value. Okay, so that's just review. So turns out there's a more general notion of measurement that is possible in quantum mechanics. And this is known as a positive operator valued measure, or a POVM. So a POVM consists in a set of positive semi-definite operators. So, recall positive semi-definite just means that it has, positive eigenvalues, basically. And there's, also a sort of more technical definition. A set of positive semi-definite operators that sum to the identity. So if you have a set of these little operators or matrices in the finite dimensional case, their sum is the identity. So here, each operator corresponds to a possible outcome of the experiment. And crucially, whereas for a von Neumann measurement, assuming no degeneracies, there would be D possible outcomes where D is the dimension of the Hilbert space. There can be like—
Matthew, 1 moment. You said that each operator corresponds to an output of the measurement. I thought that each measurement corresponds to one possible value of the operator. The operator can have many possible values. Each value corresponds to a different outcome of the measurement.
Yeah, so in this case, it's a little bit different than the usual, von Neumann case where you have one operator and the different possible, output states are given by the eigenvectors and so forth. Here, each of the operators represents a possible outcome. And we'll see how that cashes out in a little bit.
Okay.
And what does positive mean? What's positive?
So positive semi-definite basically means that it has positive eigenvalues.
So you can't get a
Or
negative velocity?
it's—
You can't get a
Sorry?
negative velocity?
So again, we're not looking like the possible values of the observable as being like the eigenvalues here. Rather, each of these operators corresponds to an outcome.
Can I follow up with a silly question?
Yeah, sure.
Not silly. Whichever interpretation of quantum mechanics you believe, the eigenvalues correspond to actual observed measurements, verified by empirical evidence, whether you believe in Copenhagen, Bohm, whatever you believe in, many worlds. So this theory is not empirically valid.
No, I'll show you how to do this. So, this is just the mathematical definition of it. I'll show you how to implement one of these. Ultimately, what you do is you take your system and you couple it with an auxiliary system and then do a normal kind of measurement on the auxiliary system. Okay. So, like the normal notion of measurement, it's like, okay, you have an observable that's just associated with that system and whatever, you take your projections. Here, the idea is you're considering a more general case where you're entangling an auxiliary system or an apparatus or something with the original system and then measuring the other guy. Okay. And again, yeah, just, hold your horses.
Matthew,
I'll show you how to do this.
Let me just clarify for the first question that was related about the eigenvalues of an operator and the measurement. Basically, when you have eigenvalue in an operator, there is also eigenvector, and this defines a subspace, and you can associate with this eigenvector actually a projector that would be the operator effectively that you can measure, and then it's the only value you would have. So in this respect now, if you look at the projector as operator that you are measuring, this goes back to the operator kind of definition that Matthew was talking. And I see down there, he has the pi for the projectors.
But this seems to be a circuitous route that's unnecessary since the eigenvalues give you the only possible measurements.
Well,
Right,
I'll
but
show you why.
The point is that from a vector, you can go to operator, and then you can formulate everything in terms of operator acting in a space, an algebra of operators, and then you can ask, how do I represent this algebra in different spaces and what do I have there, which is much more general, just looking at a specific realization.
Let me make a suggestion that we let Matthew finish the presentation of POVM, then we can discuss it. I'm really curious to know what it is.
Yeah, and I'm still
Thank you,
curious
yeah.
to know what positive means.
Oh yeah. Well, yeah.
It's the opposite of
Well,
negative.
Positive definite. Yeah, well, what was the technical definition? It's like the inner product is always positive or zero. And that ultimately amounts, to having, non-negative eigenvalues.
Yeah, so we can associate with this probability.
Yeah. Yeah, and also, Vesselin, yeah, your point about, associating projectors with the different vectors, the outcome vectors, it's like each of those in itself is like a measurement, a kind of yes/no measurement that you can make on the system. So whereas for a normal von Neumann measurement, there can be like, assuming no degeneracies, D possible outcomes, where D is the Hilbert space. You could have any number of outcomes to a Pavlov measurement, as long as these associated operators sum to the identity. But similarly, the probability of a given outcome is given by the trace of one of these operators on rho. So the question of, so what's the resulting state, after you do the measurement? In the general case, you can basically, the idea is like to split apart each of these operators into two pieces called Krauss operators. So that applies to the general case. We're going to be considering a very special case of a very special kind of Pavlov, where that actually sort of simplifies. And you can just treat these operators, they each have an associated projector with them in this very special case. So I'll sort of come back to this.
Matthew, I just missed it. Where does the auxiliary system come in? I just missed it.
Yeah, okay, so maybe I should, let me get through one more section and then I'm gonna skip ahead and I'm gonna tell you how to do that.
Which Krauss does that refer to? Does that refer to Lawrence Krauss?
Oh, I don't know, actually.
Or his great uncle Irving?
I don't know. I don't think it's Lawrence Krauss.
Because Lawrence Krauss came up last time, the dispute that Albert had with Krauss.
Yeah, for sure.
Anyway, never mind.
And by the way, just to, provide a little bit of a frame of reference, we've already seen things like this before. When we talked about spin coherent states, we found that each of the totality of spin coherent states for a given J value form an overcomplete basis or frame for spin states. And in that case, there's like an infinite number basically of elements. And you integrate all of them and you get one. Okay, so the key here is that we're not just going to consider any Pavlov, all right, but a very special class called seq Pavlovs, which stands for symmetric, informationally complete positive operator value measure. Okay, so they've been conjectured to exist in all dimensions, and numerical evidence suggests this is the case, although like a big thing in the Cubist community is the desire for a proof of that, basically. So if you can do that, they'll be pleased with you. And as I say, numerical evidence suggests that they exist. Okay, and we have a list of them, the ones that people have constructed, so we'll see that. So, their defining property is that the Pavlov elements can be written as themselves projection operators. So, whereas like a normal Pavlov can have, any number of elements, these seq Pavlovs have exactly D squared elements, okay, where D is the dimension of the Hilbert space of the original system. And so you get a set of D squared, basically states, and you can form the projectors associated with them. And if you take the trace of, each of the projectors on all the other ones, then of course it's one in the case that it's, the same state. But otherwise, it's going to be given by this this expression here. So you get basically 1 over D plus 1. Okay, so the inner product of each of these states with the other states that like aren't the same one, they're all even, and that's the symmetric part of symmetrically informationally complete, whatever. Okay. So such a set of projectors will be linearly independent. And if you rescale them by 1 over d, they will form a Pavim in the sense that you add them all up and they give you the identity. And now, like, here's the sort of the punchline. Here's the motivation, like why we care. I mean, there's a lot of interesting reasons to care, but basically, a seek Pavim specifies a measurement for which the probabilities of the outcomes specify the density matrix or the state itself. Oh wait, my earbuds just made a funny noise. I have to do something about that. Ah, my apologies. Hello, wait, someone say something. Can you hear me?
Yeah, I can hear you.
Yes, can hear
Okay,
you.
okay. All right, we're good for now. All right, so if all right, I might have to go get other headphones in a second, but let's go on. Okay, so a seek Pavim specifies a measurement for which the probabilities for that one measurement nail down the quantum state completely. So like in contrast, you know, if you're like considering a qubit, say, you want to nail down what is its quantum state. You'd have to take, you know, basically 3 separate expectation values. Take, you know, do 3 different experiments again and again. Measure in the x direction, measure in the y direction, measure in the z direction, or whatever directions you want. And then, you know, from those 3 numbers, you could get the state up to phase. So we'd have to repeat many times 3 different non-commuting measurements. But for a seek Pavim, the probabilities on each element of the Pavim fully determine the state. We're talking here about a single kind of measurement. And basically, you know, the motivation is because of that, we can then sort of reformulate quantum mechanics in a way that looks like very, very similar to normal probability theory. Because we can associate the state with a probability distribution on these seek Pavim outcomes. Yeah?
Matthew, so correct me in my understanding of what you just said. If I have a particle in a box and I measure the probability of each of its positions, I prepare it, and then I measure its how often it shows up at 1 inch, at 2 inches, at 3 inches. That seems to give me the state. But now, if the particle was a fermion, and I want to know its spin, how that doesn't seem to have given me the information for that. So in one case, it seemed like a set that fulfilled your criteria, but then I could be surprised and find out it wasn't.
For sure. Well, I mean, I would say that like the, you know, insofar as like the, you know, the position and the spin like live in different Hilbert spaces, you're not necessarily going to get information about the one from the other one. But, you know, more generally, like, you know, this is not the case. So like a position measurement, you know, is like a von Neumann type measurement, like in theory, right? This is like a, you know, a slightly more general framework. So again, like, so, you know, we imagine, you know, taking that particle in a box, like entangling it in a special way with some other thing, and then doing measurements on that guy. And it's those probabilities. So it's not so much like a set of probabilities, say like for positions. And again, I will show you how to construct the, you know, that like the entangling operation in just a second. I just want to like explain a little bit like how to just show you how to like work with them first, and then we'll do that because it'll just become like easier to see. Chris Fuchs and collaborators have put online a repository of seek Pavims, and you can download them. Here's a link. You'll get a zip of text files, 1 for each dimension. And so I'm just going to explain like how to you know, work with these. So each text file contains like a single complex vector, which is called the fiducial vector. And from this vector, the rest of the seek elements can be derived. So how do you do this? first you define with actually, the famous, 19th century mathematician Sylvester, the clock and shift matrices for a given dimension. And ultimately, this is going to give you a representation of like the Weil, Heisenberg group. So the idea is that you have Z, which generates basically like finite dimensional like translations. So this is just sort of like a, and then you have its sort of conjugate operator X here, where omega is a little root of unity, and they go along the diagonal. And so these are kind of like position and momentum. Like normally position momentum, the commutators like I or whatever, and that can only be satisfied, by infinite dimensional, differential operators, etc. These guys apply to finite dimensions, and they commute up to a phase, basically. So, we can easily define these clock and shift matrices. If you like look at what this does, it basically takes like the vector 1, 0, 0, 0 to like 0, 1, 0, 0. It's like shifts it, okay? So you get your clock and your shifts, and then you can define displacement operators.
What does the clock do? What does the clock do?
The clock is like, yeah, what does the clock do?
It tells time.
It tells
Is
time.
that clock or crock?
Yeah, I guess it's like, well, I mean, if this kind of does translations, then I guess this is something analogous to, I guess, boosts or whatever, if you want to think about it that way. So okay, so you can define these displacement operators for A and B, where A and B range from 0 to D. And there's going to be D squared of those guys. Then you basically load up your fiducial
Can you
vector.
go back to the definition of the displacement operator?
Yes, sorry.
Okay, so here you have the X and Z from before. What does it do exactly?
Yeah, it's kind of like if you think about this sort of like almost like a phase space kind of thing going on. Like these will like generate like displacements kind of like in this phase space. I think is the best way of thinking about it.
Matthew, which one was the clock matrix? Which operator is it?
Yes. So Z was the clock. No, Z was the shift, and X was the clock.
Okay.
Okay, shift is more reasonable than translation. It is like a shift register here.
Yeah, for sure.
And clock, I still do not see very clearly why you call it clock. What is clockish about it?
Well, I guess if you think about omega like frequency and time, then when you do a measurement and get one of these diagonal elements, it tells you whether it's the first, second, third. I mean, basically the power is the cycle number.
Yeah, that's good, totally. So once you got these guys constructed, you load up the text file, extract the fiducial vector, and then act on that vector with each of the displacement operators. And then you'll get D squared vectors. And if you form the projectors associated with them.
How do you get the fiducial vector? Can you repeat how you get the fiducial vector?
Ah, yes. Well, you rely on the ingenuity of others. So like, okay, if you look at the bibliography at the end, there's various papers where people like describe how they calculate these. They use various supercomputers, at the whatever. A lot of these guys are at the University of Massachusetts, Boston. So in any case, on this website, you can, they've calculated them for you basically. And so you just download this file and they give you the vectors.
Matt, what is the etymology of the term fiducial? I've only seen it come up in terms of financial responsibility.
Yeah, so like in this case, it's
What
like
does that
a
mean?
kind of reference. It's like a reference vector. So it's like in terms of this one, like once you've nailed that down, you can like define the other ones like with reference to that.
So it's got responsibility for all the other vectors,
Yeah, for sure.
something like that.
Okay, what are the properties of a fiducial vector? How would I know a fiducial vector when I see one?
Yeah, for sure, for sure. Yeah. So again, I refer you to, in particular, the paper. So this one provides a good overview here of sort of like how they went about calculating them, and you know, the various open conjectures about them, and that sort of thing. So I recommend that. So, okay, getting there, where are we? Okay, so this construction works because the Qbisms, at least the ones that people know about, are group covariant under the Weil-Heisenberg group, okay? And as far as anyone knows, this construction works, although there's some interesting exceptions. So like I just mentioned, for example, in dimension 8, there's also like another Qbism that's, you know, covariant under a different group, tensor product of 3 copies of the Pauli group. And there may be other exceptions. This one, there's some interesting, you know, sort of theory about how it relates to the Octonians. And again, I refer you to the papers for more, you know, fun with regards to that. And so once we've done this, we've loaded up our fiducial vector, applied, you know, the d squared different displacement operators, we get our seek states. And we can test that they have this defining property. Oh. Jupyter Notebook, sorry, load, there you go. So again, you know, the idea is that the inner product is, you know, even across like all of the different vectors. And that is what we find. Now, like for some geometrical intuition, which is always important.
What does even mean?
Yes, so that like when you take the, you know, the inner product with, you know, like a vector with itself, it's just 1, but all of the other inner products are all the same. And specifically, they're 1 over d squared, d plus 1, sorry, 1 over d plus 1. So in the case of 2 dimensions.
Matthew, it is not 1 over d plus 1, it is 2 over d plus 1.
No.
No, because this will be when, you know, when these are equal, when these are not equal, that's 0. So then it's just 1 over d plus 1.
So what makes it even?
Oh, just that they're all the same.
The normalization is made so that the product between 2 different vectors, operators, gives you the same number, and this is just 1 over the dimensionality of the space.
So for, you know, in the case of 2 dimensions, we can have a nice, you know, visual sense of what these vectors look like. And they form a tetrahedron in the block sphere. So, you know, these are the 3, you know, the 4 states that you get. So, you know, whatever one of these was the fiducial vector, and then acting on it with the different displacement operators, or I guess what, well, okay. Acting on the fiducial vector with the 4 displacement operators gives you these 4 vectors, which form a perfect tetrahedron in the block sphere. And so, you know, okay, you know, you're trying to imagine that in higher dimensions, and, you know, just picture something really symmetrical. All right. And, you know, in general, yeah, like in higher dimensions, the study of these things is like a very interesting geometrical problem involving maximal sets of complex equiangular lines, which apparently has all sorts of interconnections to different parts of mathematics. And again, that paper goes into some of them. Okay, so
I think one important point to kind of make here is that you have to break away from your usual orthonormal thinking, where two vectors are orthogonal. That means that their product is 0, and then you can normalize each of them, so you have n vectors that are all normalizable and orthogonal to each other. But if you go back on the definition, I mean, for the trace of the two projectors, you can see that actually you are not asking them to be orthogonal. You're just asking them to have overlap that is non-zero. And then eventually you can go through the lists and make sure that this overlap is always the same.
yeah, totally. Yeah, one has to get away from the sort of usual way of thinking about, bases and so forth. These are like most assuredly not orthonormal set of vectors. And yet we can still use them to, as I say, fully determine the quantum state.
And whereas a normal basis has the dimension, has a number of basis elements equal to the dimension, this one always has one more.
The d squared actually.
Oh, d squared. So what we're looking at, this case here is a two-dimensional?
Yes, so this is 2 dimensions, and so there's 4. And in general, like a Pavim can have like any number of elements. It's, specifically in this case of the seq Pavims that you have d squared. Okay, so, all right. So once we have a seq Pavim, so this just once you've loaded in the seq states, this is just a function that just packages it up as a dictionary. Here's the states, here's the projectors, and then recall that the actual Pavim elements are the projectors rescaled by 1 over d, so that they sum to the identity. And we check that they sum to the identity here. So suppose we have a density matrix. We can, and a seq Pavim. We can expand it in terms of the seq Pavim elements via the trace. And we can get a set of probabilities. So we just take the trace, which with each of the Pavim elements, and indeed, these are probabilities between 0 and 1, they sum to 1, etc. Moreover, you can go in reverse. So, given a seq Pavim and a set of probabilities, okay, and there's a footnote here that we're gonna come back to, we can uniquely reconstruct the density matrix with this formula. So here, Pi is just this vector of probabilities. And, recalling that, so these big pi i's are projectors onto the seq states. The seq elements, recall, are 1 over d times those projectors. And because the sum over all of those elements is the identity, we can, just sort of simplify that formula here as just rho equals d plus 1, sum over I of the probabilities I times the projector I, and then all that minus the identity. And so you can see that, given a density matrix, we here calculated the probabilities. And then here we just, applied these 2 formulas in succession, just for the sake of argument, and recover the original rho. So we take rho, get this bunch of probabilities, and then we can go backwards. From the probabilities, we can reconstruct rho using this formula. And most of the formulas actually that we're going to pay attention to, and what in the next couple sections, they all kind of look like this. So get used to this little guy here. Got like a d plus 1 over here. Okay, you'll see. All right. Well, actually, let me skip forward a little bit, just because there were so many questions about how to actually implement these Pavims. Now perhaps would be a good time to actually just show that, because the next section is going to get into kind of the meat of the quantum stuff. And or the sort of the probability stuff. So let's just talk about this really quick, just to lay those questions to rest. So, you know, suppose we have a quantum system, it's got a Hilbert space, dimension d, and then we have a problem with n elements. In the case of a seq problem, we'd have d squared. We then adjoin an auxiliary system with Hilbert space dimension n. In other words, our auxiliary system has as many basis states as problem elements on the original system. So now we're working with the Hilbert space, you know, of dimension d, tensor Hilbert space of dimension n. Then we can define projectors onto the basis states of the auxiliary system, just like working in sort of the computational basis. Just write them like this: identity on the system, and then just the outer product of the basis states. Let's say.
Matt, I'm sorry. You know, I'm trying to. It's hard to see. This is very small, but I'm trying to follow it on. I'm trying to follow it on the you know, your file that you.
Oh yeah. I should put a little.
Where is this? About halfway down? Roughly, where do we find this?
Yeah. Good point. Yes, it's about 3/4 down, I believe.
3/4 down on the notebook.
Yeah. Interlude, implementing problems.
Oh, okay, I got it. Thank you.
Yeah, sure. So, so we can define projectors, you know, onto the basis states of the auxiliary system. We then have our elements of the problem, write them here like EI. We can then construct an isometry, okay, which is a sum over the problem elements, square root of the problem elements, tensored to the basis state I of the auxiliary system. So here I, you know, is labeling both problem element and also a auxiliary basis state. We've chosen this cleverly so that any element of the problem can be written like this. So we can rewrite the problem elements in terms of this projector onto the auxiliary system, wedged in between V dagger and V, where this is this isometry. So here, this just, you know, loads in a problem. We construct the projectors. We construct the isometry. You know, this is just translation directly of this formula in the code. And then we check that actually this expression does in fact recover the original problem elements, and it works. So now we have this isometry that takes us from the Hilbert space of the system to the Hilbert space of the system tensored with the auxiliary. We can then extend this into a unitary that takes us from, you know, the tensor product of the two Hilbert spaces to the tensor product of the two Hilbert spaces, you know, using the QR decomposition. So essentially, you know, we're using the Graham-Schmidt procedure to like fill out this rectangular matrix, the isometry, into a square matrix by adding in like a bunch of extra orthogonal columns. And then actually, you know, you have sort of, you know, rearrange the columns so that the columns of the original V appear every nth column in order to take into account the tensor product structure. But you know, that's just detail. So, you know, we take our V, do the QR decomposition, you know, thanks NumPy. And then this should satisfy, if we have this unitary, the unitary acting on the identity tensor, the sort of like the vacuum state or the zero state of the auxiliary system should recover the original isometry. And that is the case. Okay, so here's the finale. We already know how to calculate, in the way given above, the probabilities for each of the problem outcomes. It's just the trace of the problem element on row. So to actually implement this, what you do is you start off with your auxiliary system in the zero state, so that the overall density matrix is, you know, the row of the system tensored with the, you know, outer product of the zero state. We then evolve the system and the auxiliary with our unitary that we just constructed. And then we perform a standard von Neumann measurement on the auxiliary system. And, you know, recalling our definition of the projectors, we can then sort of write the same probability in a different way. So we take, you know, row and the zero state tensor together, evolve them with the unitary, and then do the projection, take the trace. And you can see that we get exactly the same probabilities.
Question. It says first line, in some sense, the difference between classical and quantum is summed up in the difference between these two formulas.
Oh, we haven't gotten there yet.
I'm sorry. I'm sorry.
Yeah, that's yeah, no, I mean, yes, that will come, don't worry. Furthermore, the question of, the state after measurement, in this case for like the seek problems, because of this property that they're like rank 1 and so forth, we can see that if we look at, like suppose we, suppose we, did the measurement on the auxiliary and got like the 0th basis state. If we then looked at, what state is the system in, we can see it's in exactly the state associated with the first projector of the problem. So, okay, so that, all right, so it's sort of not entirely practical. I mean, you got to figure out how you want to implement this unitary on your quantum computer or whatever, but just to make concrete, like what in practice, are we doing here? Basically, ultimately the problem cashes out at a certain unitary operator that entangles your system of interest with an auxiliary system. You do a standard measurement on the auxiliary system, and you get the probabilities from before. So that's the sense in which it's a generalized notion of measurement. Okay. All right, so now we get into the kind of the meat of the discussion here. All right. So we have so we're going to consider the following situation. We first make a seek problem measurement, and then we're going to make a standard von Neumann measurement on a given system. And just to kind of keep this straight and following the vivid imagery of Fuchs and many of his papers, we're going to refer to the seek problem as being up in the sky, and the von Neumann measurement as being down on the ground. And we're basically going to consider two different situations. On the one hand, first doing this problem measurement in the sky, and then doing the von Neumann measurement on the ground. And then we're going to consider the case of like directly just going and doing the von Neumann measurement. And we're also going to consider the case where we have a problem in the sky and then also another problem on the ground. So we're going to consider those different cases. And so we're going to contrast what happens, basically in those two different stories, where on the one hand, we do a seek problem measurement and then a von Neumann, versus the case where we go directly to the von Neumann. So in this first case, doing the seek problem and then the von Neumann, we say want to calculate the probabilities for the von Neumann measurement. Okay, so already given our state row, we've calculated the probabilities for each outcome of the problem. Now we'd like to assign probabilities for the outcomes of the von Neumann measurement. Okay, so what we need are like the conditional probabilities, the probability of the von Neumann outcome J, given that the seek problem returned I. And then the probability of the jth outcome of the von Neumann measurement is just given by this. This is just standard probability, the law of total probability. Probability for an outcome J of the von Neumann measurement is just a sum over the conditional probabilities for J given I multiplied by the probability that I occurred. So, in terms of the quantum formalism, the standard way of thinking about this would be that like after the seek problem measurement, we update rho to now like a probabilistic mixture of, the outcome states here are big pi here, each weighted by the probability that that outcome occurred. So, rho becomes a sort of classical, mixture of outcome states weighted by the probability of them occurring. And then the probabilities for the von Neumann measurement are just if pi with a tilde is a projector associated with the von Neumann outcome, then we just take the trace of those projectors on this updated row, and we get the probabilities for the von Neumann. So here
Matt,
we
is this essentially where a Bayesian probability comes in. In other words, the new probability depends on the prior. Is that?
No, this is just conditional probability, I think.
This is just conditional.
Right. So we're going to see. So yeah, we'll come. Yeah. Let me get through a little more. You'll see the motivation for starting here. So here's just a translation of what I just said into code. We have just some random von Neumann observable. We formed the projectors. We then already have our probabilities for rho. We calculated them up here on the different Popham elements. And so, we can form the density matrix after the Seek-Popham measurement, and then we can get the probabilities for the von Neumann, and we get this. Alternatively, however, we could form the conditional probabilities directly. Okay, so we can fill out a matrix here, RJI, where we take the trace of sum over, the trace of where pi, recall, is a projector onto the Popham element, and pi tilde is the projector onto the von Neumann. And then we can directly use that formula from before, this sort of law of total probability thing. And so this is just, again, a translation of that into code. And you can see we get the same probabilities as before. So the only difference here is we were just working directly with the density matrix here, kind of updating it, whatever. Here instead, we stick with our probabilities. We already had those. Recall it's just the trace of the density matrix with each of the Popham elements. And then we calculate this conditional probability matrix by looking at the relationship between the Popham projectors and the von Neumann projectors. And it amounts to the same thing.
Matt, can I ask the question that I was going to ask before? I jumped ahead to that line, that in some sense, this measures the difference between classical and quantum.
Yeah, well, we haven't gotten there yet. We haven't gotten to the second formula. But
you say that right here. It says here the difference is where is it? I just saw this. The point is that
it's coming up. It's coming up.
Okay, I'll save it.
Yeah. Just like 5 more minutes. You'll see. So I just want to say, this matrix of conditional probabilities is indeed, a conditional probability matrix. Its columns all sum to 1. And by the way, this is not that important, but we don't need to confine ourselves to the case of a von Neumann measurement on the ground. We could also use another Popham. So we do a Popham measurement and then another Popham measurement. And it's basically the same idea. We can either update our density matrix and then take the trace of the second Popham elements with the updated density matrix and get the probabilities for the second Popham. Or we could take these traces with each of the Popham elements of the first guy and the Popham elements of the second guy, and then get a matrix of conditional probabilities and do the same thing. And you see that these give you the same. So just one. Okay, so all right, so now we're going to get to what Michael was just alluding to. Okay.
So let me before you get to that though.
Okay.
The expectation value of the quantum measurement is generally the same as the classical value. So how does that all
it can
jive?
be.
Sorry?
Well, it can be, it isn't always.
Okay, so in some sense, this measures the difference between the classical and the expected classical and the quantum probability. Because you mentioned that.
You'll see.
Yeah. Okay.
Yeah, we're about to get to that. So that's what this. Okay, so this is the punchline here, right? So before we consider the case, we have a system, we set it up in the sky, do a Seek-Popham measurement, and then we do a measurement on the ground, either Seek-Popham or von Neumann or whatever. But now let's consider the case where we didn't do that Seek-Popham measurement first. We go directly to the von Neumann measurement. what would the probabilities be? Well, we all know, no mystery there, right? It's just the normal thing. We take the projectors corresponding to the von Neumann outcomes, take the trace on rho, and we get the probabilities. Duh. Okay, now here's the thing. It turns out that we can get these probabilities in a different way. They can be obtained from this formula. So here, Pi are the probabilities for the Pavim outcomes. Rji are the conditional probabilities of the von Neumann measurement given the Pavim outcomes. So it's like really similar to this formula, okay? We're like describing these probabilities directly for the von Neumann measurement in terms of the probabilities for this now hypothetical Pavim experiment up in the sky and the conditional probabilities of, you know, suppose you got a Pavim outcome, then you get a von Neumann outcome. And you can see, you know, just like it's very similar indeed to the formula here for reconstructing the density matrix.
So wait, somebody say something. My earbuds just died. Is it?
Hello, Tess.
Oh, good, good. Okay, everything's fine.
But you're not, it's hard to hear you now.
Oh,
But we can hear you still.
boy. Okay, okay. Thank you. So this looks like incredibly similar to our formula from before, okay? But there's this little d+1, and there's this little -1. But behold, you get exactly the same probabilities. So this, you know, which is just like the normal way. You have like a density matrix, you want to know the probabilities for the von Neumann outcome, you take the trace of the projectors on the density matrix, whatever, no need to talk about anything else. We can equivalently get those probabilities with reference to this sort of Pavim measurement, which here like remains completely hypothetical, but it's like we have a bunch of probabilities for outcomes there. We have some conditional probabilities for the Pavim, for the von Neumann given the Pavim, and we just sort of change the law of total probability. We just deform the law of total probability ever so minimally. Just add a little d+1 here, a little -1, and we can get exactly the same results. In other words, we can express the usual quantum probabilities in the case that we go directly to the von Neumann measurement in a way that looks like ridiculously close to the usual formula, involving probabilities for the Seek-Pavim outcomes, conditional probabilities for the von Neumann outcomes given the Seek-Pavim outcomes. We sum over hypothetical outcomes of the Seek-Pavim, multiplying the probability of each outcome given our state rho by the conditional probability for the von Neumann measurement given the jth outcome, given that the Seek-Pavim outcome was I, except that the form is somewhat deformed by d+1 and -1. And clearly, you know, this is equivalent to the usual Born rule, but it's expressed entirely in terms of probabilities and conditional probabilities, like no amplitudes, okay? And okay, it sort of makes sense that you could do this, right? Like we've said, the probabilities on a Seek-Pavim measurement suffice to nail down the quantum state. So like, it kind of makes sense that you would be able to, you know, express the probabilities for like really any experiment in terms of those probabilities, the probabilities with reference to a certain Seek-Pavim. And when you know, work it out, which, I mean, I didn't prove this, but, you know, again, I refer you to the papers for that. It turns out that like when you actually look at like, well, what would be the expression for that? It looks like a lot like the law of total probability, but just a little bit different. Indeed, we could just, you know, pick some Seek-Pavim to be our, you know, this is just my reference apparatus. I can describe any quantum state like I'm ever interested in terms of the probabilities with reference to it. And I can express the probabilities for any measurement I might do in terms of conditional probabilities, given the relationship between my reference Pavim elements and then the projectors of whatever other measurements I do. Okay, so then this is the part that you kept, that you were referring to, Michael, you know. So
Right.
you look at these two expressions, right? And it's like, what is the operational difference between them? And the difference is precisely what? Whether the seek-pov measurement has actually been performed. Like if it has, then we use this first formula. We lose quantum coherence. If it hasn't, then we maintain it and we use this formula. In other words, the difference between classical and quantum, or a lot of it at least, is summed up, so to speak, like in the very minor difference between these two formulas. So, you know, there's a slogan attributed to the physicist Asher Perez: unperformed measurements have no results. Not get too hung up on the philosophy behind this at the moment, but the point here is that, you know, classically speaking, we should be able to use this first rule, this like law of total probability, like whether or not we actually do the measurement. Like if this probability distribution here somehow sort of nails down, you know, the state, we've like identified the relevant degrees of freedom, et cetera, then, you know, that's just, you might say, like just like an objective description of like that system. Whether you actually do the measurement hardly matters, right? There's no like special notion of measurement. You just look at that as like, that's just a property of the system. But quantum mechanically, the case is different. If we don't actually do the seek-pov measurement, we can't use the law of total probability. Like if we want to use it, you know, if we want to like describe things in terms of our seek-pov and stuff, we have to use this second formula. And, you know, this sounds kind of metaphysical and crazy, like, well, what do you do? Unperformed measurements have no results. Like, what can we say about it? Well, you can say this. It's like we have something just as good as the usual law of total probability. We have this, which ultimately amounts to the Born rule in a different guise.
So Matt, other than the mathematical gymnastics that we performed here, what does this buy us that Copenhagen doesn't buy us, or the Born rule? What does this buy us?
Yeah, well, so, I mean, the motivation, again, you know, we haven't gotten to the philosophy of it, but, you know, the motivation of the Cubists was to, you know, describe quantum mechanics like in a way that's like as close to normal probability theory as is possible. And so, you know, I guess in some ways the idea was to sort of like banish the quantum state per se. It's like you want to kind of—
It doesn't, I mean, Bayesian probability is based on an assumption of a measurement that you're going to make based on a prior. Now, how does that come in here? Which is the prior?
Oh, well, I mean,
what, you know.
So, well, okay. I mean, like in this expression, you can look at like PI as being like a prior, and then you have this like conditional probability here. I mean, the key difference, like the whole Bayesian thing is something like, you know, even centuries ago, people were arguing about, right, like what is the meaning of probability, right? And some people were like, oh, you know, it has to do with the frequencies of things, and maybe those frequencies are like objective properties of you know, whatever you're studying. And then, you know, the Bayesian tradition tries to look at, you know, probabilities, you might say, in the wild, like in flux, that like the idea is that like what probability theory really is a way of like, okay, you have some priors, you get some new evidence, you like assign new probabilities, and that probabilities really measure the strength of your belief.
Right. Well, Bayesian is based on prior measurements. You make assumptions based on what you've measured before. But that's not true of quantum mechanics. A new measurement is not based on what you measured before. So I don't understand how it all fits together.
But I'm not sure what you mean by that.
Well, in quantum mechanics, the measurements are independent. You don't have a prior.
Not quite. In quantum mechanics, if you measure the spin up in the z-axis, next time you measure the spin in the z-axis, it will again be up.
Absolutely. Absolutely, but that has nothing to do with probability. Your probability is 100% in that case.
Yeah,
You've already made the measurement, and if you measure in the same direction, but then if you measure in an orthogonal direction and then come back to the original direction, it's you're back to probability. The spin is not guaranteed to be up.
So I mean, the essence of the
So how do priors come into this? I mean, your previous knowledge of what you measured has no effect on the new measurement if they're orthogonal directions.
well, but I mean, that's like a prior, right? Like, okay, I know that I did an X measurement, so then like I know I can then say like, well, for the Z measurement, I'm gonna assign 50-50. I mean, I'm not sure what you mean. Like,
no, if you do a measurement in the X direction and then you measure in the X direction again, you'll get the same measurement. But if you then go and measure in the Z direction and then come back to the X direction, it's back to 50-50. So the prior, I mean, I agree with Moshe's point, but I don't see where it's relevant here. In other words,
well, actually, the thing is that he has to get to the time evolution. Basically, what he was showing you, there's two pictures. The picture where you have the standard operators and von Neumann projectors and density matrix expressed in terms of von Neumann projectors. And then you have these new operators that are not orthonormal anymore, but you can still define the probability and density matrix rho prim. And you can see that these two matrices are actually very simply related with d plus 1 and minus 1 if you go through the expressions. Rho and rho prime are related. And this basically is saying you can do the von Neumann projectors, or you can do the Sig-Poven picture. And how do you switch from one to the other in terms of probabilities? And then you need now to go to the time evolution to see what is happening if you have evolution and then you switch during evolution.
yeah, I understand, but how does an actual prior measurement, in other words, your experience of measurement, affect a new measurement?
well, so I mean, that gets at
That's what Bayesian is all about.
right. Yeah. So I mean, it's like you bring your priors to the situation. I mean, and then you.
But this is called in RJI, because this is saying if you did a von Neumann measurement and now you're doing a new type of measurement, I mean, that's the conditional probability there.
But is it meaningful if your new measurement is in an orthogonal state?
Well, again, we're considering here like these Pavim outcomes are not orthogonal.
Oh, so in other words, they're in states that differ by less than 90 degrees. In which case, even classically, if you make a measurement in the X direction and it's up, spin up, and then you measure at a 45-degree angle, the X component will be up. But if you measure at 90 degrees, then you've destroyed the previous measurement. But anyway, this is.
I mean, I think that, yeah. So there's two things I think going on here. Like one, is like the motivation here is to express quantum states and all the different, types of reasoning that you can do with them, not in terms of probability amplitudes and the usual von Neumann kind of measurement. Instead, entirely in terms of just normal probabilities, which we can define in terms of these Sig-Pavims, and then conditional probabilities, basically. So we make it look very like normal probability theory. And the other thing that's going on is this question about sort of probabilities being objective versus subjective in some sense, right? And so like the Bayesian tendency is to be like, there's no like objective, like in classical probability theory, like the Bayesian would say, there's no like objective unknown probability distribution. There's just like the process of you constantly updating your beliefs in the face of new evidence, and the fact that, you know, probability theory sort of allows you to impose coherence or consistency on your different beliefs so that nobody can make a buck off you, okay?
But Matt, with respect, Bayesian applies to classical measurements. You're updating, but like I said, in quantum measurements, once you make a measurement in an orthogonal direction, then your past experience is meaningless.
Well, so, but like, there's two senses of that, right? It's like, it's meaningless in the sense of now the outcome's 50-50, but
Right,
it's
you're
not
back
meaningless
to-
in the sense
you're
that you're
back to square
conditioning on
one.
the fact that you did that measurement, and so now you can assign 50-50 to those outcomes or whatever.
Oh, okay.
Actually, that's not quite true. That there was an interesting paper that was published by IBM researchers, where they were claiming that they can predict what kind of jump would happen based on the fact that whether it was happening or not, what was the configuration of the system. So that I think they were calling it like catch a quantum system during a jump, something like this.
Yeah. And was this based on empirical evidence or just
Yeah, experimental
theoretical?
experimental measurements.
Really?
Yeah.
I used to work there, so I may know the people.
I'll try if I see the
Yeah, if you could send
the
us
link,
all the
I will
paper.
share it.
Yeah, if you could
Please
post
do.
the paper, that would be great. Thank you.
Yep.
So you might wonder, you know, we just considered the case of a Pavim measurement and then a von Neumann measurement, either whether we, and then the case of whether we actually do the intermediate Pavim or not. This is just if you're wondering, you know, what if we had, instead of a von Neumann measurement being the second measurement, what if we had another Pavim, okay? Or another seek Pavim specifically. These formulas, by the way, I should mention, they apply in the case where you're using a seek Pavim, not in the general case of a Pavim, or, you know, there's other like kind of intermediate things. So you can have kind of like mutually unbiased sort of Pavims that like aren't symmetric, but are informationally complete and like in another sense. And the formulas look a little bit different. So I just wanted to mention that, you know, if you do look at the literature. But in the case where, you know, you do like a seek Pavim and then another seek Pavim, you would use this formula. Sorry, if you know, don't do the seek Pavim, the intermediate one, but you want to describe the probabilities for your other Pavim in reference to your reference Pavim or whatever. So, you know, we can see that you can get the same probabilities either by just you know, calculating the probabilities given your second Pavim with rho, or using this formula, which, you know, it's just analogous to this one. But, you know, similarly, you know, you get this sum, you have d plus 1, but instead of just minus 1, you just like have this little extra bit here. So, and then another point is that, you know, you can express all these formulas in like very compact matrix form. If you, you know, define M to be d plus 1 times the d squared identity matrix minus 1 over d times J, which is the d squared by d squared matrix of all ones. And then if you have R being your matrix of conditional probabilities, P being the vector of probabilities for the reference Pavim, then the vector of values for the you know, outcomes to the other Pavim are just given by this expression here. So we get the same thing as before. Here, yeah, you know, this is where we're considering the case of a von Neumann or a Pavim, and the same thing. Like, you know, you get the say probably 6831. Where was it? 6831, etc. We had 19, etc. 19, etc. And then, you know, here it's just very nice to see. It's like you get like, so, you know, this, you just take R on M on P, and that's the case where you didn't do this intermediate measurement. Okay, so this is just the normal Born rule in disguise. But then if you did do the intermediate measurement, it collapses to the classical case, usual law of total probability, which amounts to just not using the matrix M and just taking R on P. And you get the right answers. So then, it's kind of interesting. You can consider, time evolution in this picture. So, we can take rho and evolve it with some unitary. And, naturally we can calculate new probabilities, like with reference to our seek problem. So, we just evolve rho and then get the new probabilities with respect to this reference problem. But we could also express this in terms of conditional probabilities. So here, it's like we're getting like a conditional probability matrix, where we're taking like the overlap of like the original projectors and the evolved projectors. And then we can write kind of like an analogous formula for the probabilities after the time evolution. And you can see that they give you the same thing. And so we can compare this to the standard rule for like stochastic evolution, like in probability theory. Here normally this would be, so in this case, UJI is like in fact a doubly stochastic matrix. Its rows and columns all sum to 1. And basically this would be the classical formula, and then the quantum formula is given by this. So, we can express the quantum time evolution in a way that makes it, look very, very similar to like normal classical probabilistic evolution. I'm going to skip this section because it's like a little bit irrelevant, and just go on to here. So you can express, so again, motivation here, making quantum mechanics look like normal probability theory. You might wonder, can we express the inner product between two density matrices solely in terms of their probability vectors on the seek-problem elements? And you can. So, given two density matrices, rho and sigma, the trace can be expressed as basically the inner product of the probability vectors weighted by d times d plus 1 minus 1. And indeed, that amounts to the same thing as just taking the trace rho times sigma. Kind of cool. But this brings up an important point. So suppose we have a seek problem with d squared elements, which provides d squared probabilities that completely nail down the quantum state, which is normally given as a d by d density matrix. But you might wonder, like, what if we just start off with any old random vector of d squared probabilities? Okay, like so far we've like started with the density matrix, showed that we can get these probabilities, and then we can always recover the density matrix in terms of those probabilities, and then in terms of those probabilities, and then the conditional probabilities, we can describe these different measurement situations, the sort of case of an intermediate measurement, which looks sort of classical, the case of no intermediate measurement, it looks quantum, there's coherence, et cetera, et cetera, et cetera. We might wonder if we just start off with like any old vector of probabilities, will we always get a density matrix from them? If so, I mean, that would be great, right? Does any assignment of probabilities to seek problem outcomes specify a valid quantum state? And there's a catch, which is that like it's not strictly true that that will be the case. In other words, any probability assignment will give you a row that is Hermitian, that is trace 1, but in general, it won't be positive semi-definite, which is a requirement for density matrices. Might end up having negative eigenvalues. And since the eigenvalues of rho are supposed to be probabilities, this is a problem. And so you need another constraint. In other words, the actual quantum state space is a proper subset of the probability simplex over d squared outcomes. And so in one of these papers, you're interested in the kind of theory of this. this one, Introducing the Qplex, a novel arena for quantum theory, goes into some of this stuff. So where was it? So, this is just from that paper. So insofar as pure states are, satisfy certain constraints, when you express them as Hermitian matrices, we can sort of, write down like conditions, try to like take the compass of what this subset of the normal probability simplex looks like, the sort of subset that corresponds to valid quantum states. And you find that, it's got, they sort of have to satisfy these two equations. Just for flavor here. And if you consider the expression for the inner product here, then, insofar as the inner product between two quantum states like has to be between like 0 and 1, it has to be the case that like the inner product between the probability vectors has to be bounded in this way. And so, in this paper, they go into this, they'll say, like, if you have two probability vectors, we'll call them consistent if their inner product obeys these inequalities. If we have a subset of the probability simplex for which every pair of vectors satisfies these inequalities, call it a germ. If adding one more vector to a germ makes the set inconsistent, call the germ maximal. And then finally, call a maximal germ a Qplex. So the space of quantum states in the seq representation forms a Qplex, but not all Qplexes correspond to quantum states. And so the question is there a way of formulating like what is the constraint? And just to show you the conclusion, there's multiple possibilities for such a constraint, but they prove in this paper that you can pick out the quantum state space uniquely by the requirement that the symmetry group contains a subgroup isomorphic to the projective unitary group. So, I'm not going to go deeply into that. It is interesting, right? Because like you might like naively would be nice, like especially if you're working in this sort of Bayesian context where you're like, all right, I'm just a Bayesian agent. I'm just assigning random probabilities to things and then updating in the case that in the face of evidence, right? It would be kind of nice if you could just assign any old random probabilities to start with and then just like kind of condition on those. And like, yeah, you can do that, but like this Bayesian, this quantum Bayesian agent has to remember that their probability assignments have to satisfy these constraints. So there's like a lot more to say, about seq pavms and many conjectures and interconnections associated with them. But I thought to close out this sort of like mathematical part of the talk, we could use our favorite thing, the Majorana representation, to visualize, like what do these seq states look like? So as we've already seen, in the case of 2 dimensions, we're dealing with a qubit, and the seq states form a tetrahedron in the Bloch sphere. In the case of 3 dimensions, now recall, okay, the Majorana representation says, all right, you have like a 3-dimensional state. You're assuming it's like a spin or something, right? So like this is coming out of spin theory or whatever. But the upshot is that you can, whatever it is, one way of visualizing, say like a Q-trit or like a 3-dimensional system is 2 points on the sphere. So now we have, if our Hilbert space is dimension 3, then we're going to get 9 Pavm states, right? And each one is going to correspond to a 2-starred constellation. And then we can visualize that on the sphere. So here, and then we can click on these to kind of, does my clicks not work? Oh, that's sad. Oh, there, it does work. Yay. So again, so there's 9 3-dimensional states. Each 3-dimensional state corresponds to 2 stars. So here's one of them, the red guys. Okay, that's one of the seek problem states. Purple guy, that's another one. Green guy, okay. So we can just like look at them. Look for patterns, you know, like let's go up to like 6. Whoa, look at that. And you look at it, I bring it up because, you know, you think about like stuff like, you know, you want to take, you know, numerical integrals, you know, over the sphere or something, right? And you have to like choose some like, you know, set of points to like evaluate things at, you know, and there's like different theories of, you know, like what are the best points to choose, like when you're taking an integral over a space, like how are you gonna kind of like discretize it in various ways? And I don't know, it just strikes me looking at this image that this is like kind of like that, you know, this is like sort of like a scattering of stars on the sphere that does indeed seem to be kind of equitably distributed, so to speak. So these are, so, you know, whatever, what is this? Dimension 6. So there's gonna be, you know, 36 states, each with 1, 2, 3, 4, 5 stars. So this is one of those guys. You know, you click on this one. There's another set of states, another state, and its set of stars. Click on this guy. There's another problem state. Here's another problem state. There's another problem state. You know, kind of pretty. We can even do more. Do like 10. Oh, look at that. I mean, you can notice stuff like, look at that. Like, that's kind of interesting here. You know, we get a little circle. But like, that's kind of cool, right? Like this whole, you know, there's a bunch of seek problem states who each have a star that's like arranged in like a perfect little circle here. And then also this other like circle. But like the rest of the stars associated with those states are just, you know, kind of like scattered over the sphere. You could probably, I don't know, like, I mean, could probably, you wonder, you know, I don't have any like, I haven't proved anything about this, but like, you know, you wonder if you can kind of extract some interesting information about these guys, just like from the geometry here. You see over here too, ooh, on the other side of the sphere, you get similarly, nicely circular formation.
It looks like you could only see the small one because it was small, but there's larger circles also like that.
Right. So the idea is when I click on a star, it like shows me the other stars in that constellation, where again, each constellation corresponds to one of the seek problem states, of which there are d squared. So there you go. All right. So I mean, I guess now would be a good time for questions. I mean, so you know, the rest of the talk is like a little bit more philosophical or whatever. I mean, that was like the sort of the mathematical core. You know, we've seen how we can generalize our notion of measurement in quantum mechanics to problems where we're considering entangling our system of interest to an auxiliary system and then measuring the auxiliary system, sort of examine the mathematical apparatus around it. We've identified sort of magical and special set of problems, seek problems, the symmetric informationally complete problems. When we, you know, express the probabilities given a quantum state on the seek problem elements, we get a vector of probabilities that completely determines the quantum state. One measurement, outcomes for one measurement, nail down the quantum state, as opposed to like, say, in the case of a qubit where, you know, you have to consider like the 3 different, you know, XYZ measurements and so forth. We've then seen how, you know, we can then describe quantum mechanics in a way that looks like very similar to normal probability theory, where, you know, we can express the Born rule in terms of the, you know, probabilities for our reference seek problem and the conditional probabilities for seek problem outcomes on our reference and outcomes for any other measurement we may consider. And in order to, use it, we just have to distinguish between the case where we actually do an intermediate measurement, a seq-pov measurement, like actually do the reference, versus the case where we don't. And so in the second case, the quantum case, so to speak, we have to deform the law of total probability, and this amounts to a kind of way of sort of motivating or looking at the Born rule and what it means in a different way. So then, we can describe any probabilities for measurements we might do, in terms of these seq-pov probabilities, the conditional probabilities, and we can even describe, time evolution in terms of, stochastic, doubly stochastic matrices, for example.
So Matt, I'm not sure if you answered this, but again, my question for the third time. The philosophy, first line, in some sense, the difference between the classical and quantum is summed up in the difference between these two formulas. Which quantum? One of the probabilities, all the expected value? Which quantum?
Which quantum?
The expected value?
No, no. I mean, so we're talking about the probabilities for the different outcomes.
So this formula gives you the difference between the classical measurement and any of the probability measurements.
So like the idea is that like classically, you would only ever use this first formula, whether you actually did that intermediate measurement or not.
Well, classically, there's only one predicted measurement. It's completely deterministic.
Right, and so it's like you can look at like here. Well, how did I say it here? It's like the essence of classicality, so to speak, is that you can always regard unperformed measurements as having results. Like, in other words, classical objectivity consists in everything wearing its quote unquote outcomes on its sleeve, like outcomes or whatever. Like,
but the math predicts the outcome, and there's only one outcome.
Yeah, and so you can just speak of the properties of things. You can just say it just has a property, and the property determines the thing.
So what difference is this? It's between the classical and what quantum prediction? Any of them?
So again, so this
or the expected value.
So for the probabilities, so like, in terms of what we went through, you would use this first formula in the case where you had a system, and then you did a seq-pov measurement, and then you did a von Neumann measurement, say. And then you would use the second formula if you just did the von Neumann measurement, and you did not do the intermediate reference measurement. Okay,
so where does classical come in?
So this is so classically, you would use this first formula whether or not you did an intermediate measurement. You wouldn't have to pick out like, oh, outcomes like as a special category of things. You could just say, oh, it's like you could just say, well, like I've identified the relevant degrees of freedom of the system, and I'm just going to regard this like a property, okay? And
so then is it correct that the first formula gives you the expectation value?
It's not an expectation value. Sorry, this is the probability of the jth von Neumann outcome. So again, these are the PI is the probability for the ith seq-pov outcome. R is the conditional probability for the jth von Neumann outcome, given that you got I during the seq-pov measurement, and then Sj is the probability of getting the jth von Neumann outcome. Okay, so this is the probability of the jth von Neumann outcome in the case where you actually did the seq-pov measurement, and this is the case for the von Neumann probability when you did not do the seq-pov measurement. In both cases, we can write those probabilities in terms of the probabilities for the seq-pov and the conditional probabilities. But the difference is that in the case when we didn't do the seq-pov, we have to deform the law of total probability by just a little bit, d plus 1 minus 1. And again, this.
If I may just interject a comment, and it may be easier than to understand. Basically, when you go quantum and classical, the difference is that quantum, you can have entangled states where classically you don't. So if you consider entangled states and their projectors to be this kind of new type of measurements that you can do quantumly, then quantumly you have a little bit something more than classical. And in this respect, you can think when you have a measurement through entangled state, actually you have two possible outcomes, for example, and that they could both come out equally. In a sense, now what you have is operator that is not giving you orthonormal basis to the two other outcomes. It may actually give you up or down, depending of whatever it will come out, because you prepared in entangled state of these two outcomes. And in this respect, this kind of Qbism operators are exactly taking this property of non-pure measurements, basically that there could be entangled states that they would be representing. I don't know if you can find some literature. I guess probably there's some direct kind of expression in the same thing. One simple way to see it, if you go up earlier, Matthew, when you're defining the matrix M.
Yeah. Oh, where was it? Coming up. Yeah, here.
Yeah. So basically, you see this matrix contains, besides the identity matrix, another one, which is once everywhere. And once everywhere is very much, I mean, it has only one eigenstate, which is the eigenstate of linear combination of equal probability for all of them, which is a very entangled state. I mean, so in this respect, you can think that here you have this J operator, which represents the entangled states in your system. And you picked one that is very strongly entangled for all the possible states there.
This makes sense. Yeah, so I mean, and it's interesting because it's in some ways this, because you could say like there's maybe two distinctive things about the quantum mechanics, that both entanglement and then like also coherence or superposition, and operationally the difference between these two formulas relates in some ways to both of those things.
Well, Matthew, can we think of the simplest thing we can think of? I don't know, a Stern-Gerlach experiment. So you do an Stern-Gerlach experiment, and then there are these other measurements you could make besides the normal, whether it came in the up or down state.
Well, so it's.
So what are those other measurements? What is that? What the M represents? This other set of measurements?
So recall. So the analogous thing, like that in terms of what we were talking about, would be like, okay, you have a qubit, okay, and then to do the Qbism, the Qbism measurement, you would entangle the qubit with some 4-dimensional quantum system, and then they get all entangled, all right? And then you would do like a measurement on the auxiliary system or whatever, and so that would be like the
Yeah, I'm asking you for a physical
and then you could send it
example.
to Stern-Gerlach.
Say it again.
Like the von Neumann.
Right, the Stern-Gerlach is the von Neumann. And the question is, what is this other measurement? I understand you've come up, that there are all these matrices for them, but these operators for them, but what is a physical example So that's what I tried to think of, is the Stern-Gerlach as the simplest case. And now what would be the Harvard entangled experiment for that?
Yeah, it's a good question. So, like, well, I mean, we've seen in the qubit case, that, you're sort of amounting to, like measuring the projectors in these 4 special directions. If you form like a regular tetrahedron in the block sphere, and that tetrahedron can be rotated. If you can get the probabilities that, your qubit state is going to end up being one of those, that, it amounts to it. In the case of higher dimensions, I don't know. They're in the many of the papers, they will talk about like implementations, what I mean, of like POVMs, in general.
Can I say something? I think
Photons, you got to do this, you got to prepare it. I don't have like a concrete.
I think the Stern-Gerlach is probably not a good example, because you have to use the magnetic field to measure the spin of an electron in that case, and there's only 2 possible outcomes, and it depends on the direction of the magnetic field, which is essentially the measuring device, but sets the direction of the spin too. Maybe photons, measuring the spin of photons somehow is a better example than Stern-Gerlach. There's only 2 possible measurements with Stern-Gerlach.
Yeah.
Let me rephrase a little bit the question that Andre posed in the following way. Suppose you have an experimentalist in the laboratory doing some experiment, making some measurements, and suppose that this experimentalist just learned about this theory, about Qbism and experiments in the sky and so on and so forth. How would this affect what this experimentalist does in the laboratory? What would he do differently? Because now he has learned about all this wonderful stuff.
Right. So yeah, I mean, so it would cash out like say you wanted to do quantum tomography, right? Like normally you'd have to, like if you want to do it on qubits, you know what I mean? You'd have to, get a whole bunch of Pauli strings and, basically measure all these different, Pauli operators and reconstruct the density matrix. And so you'd have to do a bunch of different experiments again and again and get the expectation values and reconstruct the density matrix. Like again, in the case of the qubit, you'd have to measure the expectation value in the X direction, the Y direction, the Z direction. What this is saying is you could do tomography in a different way by just repeating a single measurement over and over and over again. So that, you would, given some seek POVM, you would implement, again, however, in the lab, this unitary. So you'd have an auxiliary system, the original system, and if you can manage to implement this unitary and then just measure the auxiliary system and then get those probabilities, that will nail down the quantum state.
Can you come up with a specific example telling us exactly which is the measurement that you do? What are the measurements that you do in one case, and what is specifically actual measurement that you do in the second case? What kind of apparatus do you use to do the measurement?
Okay. I mean, like, I unfortunately, I can't be like super concrete about it, but it's like, what I do here, I show you how, like, given your POVM elements, you can construct this unitary, okay? And when you construct this unitary, you like choose what the basis elements you're using for your auxiliary system. So like when I calculate it here, I just use the normal computational basis states, 1, 0, 0, 0, 0, 1, 0, 0, 0, whatever. But it could be anything. You see what I mean? So it's like, suppose it was, suppose it was, like a harmonic oscillator or something. Okay, and you had these basis states, correspond to different number states or something. Then, I would have this unitary that I would construct, and the inputs are what are the basis states of the auxiliary system and what are the Pavim elements. And then I construct this unitary, again, just like mathematically. And then I would do, in that case, a number measurement on the harmonic oscillator. And then the probabilities for the number measurement, would nail down the quantum state of the system that I'm interested in. So, it could kind of be like whatever you want, right? The challenge is just how do you translate, like I can write down a random, whatever, unitary operator, but like how you would actually implement that in the lab, how you're going to compile that down into a quantum circuit or whatever, is something which, depends on what you have in the lab or whatever. I don't have a general answer. But yeah, so it's like you can use whatever you want for the auxiliary system. You sort of just pick out, these are the basis elements, these are the Pavim elements, and then implement the unitary that you care about.
Try to think this way. If you start with von Neumann outcomes, and then you construct the von Neumann operators, they're symmetric with respect to the eigenvectors. But now you know that your space could be much bigger than just each of these pure outcomes. You can have linear combinations, and some of the non-classical ones are the entangled states. So if you start with only 2 possible outcomes, you can have 2 additional outcomes that are orthogonal, but they are linear combinations of the first 2. So you have 2 extra ones. So this basically see how you double it. D becomes D squared. And if you add these 2 other operators in your measurements and outcomes, then you're practically creating a system of sig Pavims, exactly 4 operators. Now, I'm not sure how this extends if you go to 3, 4, and higher dimensions. And this would depend very much how they construct the states, whether these are really maximally entangled states. And I guess that would be the case, but one has to look at the structure of the states.
But again, for spin half fermions, there's only 2 possible measurements. You can't construct any other measurements.
No. You're confusing the outcomes with the measurements. You're confusing the outcomes that you have spin up and down,
right,
with the measurements. But the Bell theorems and the constructions that are usually done is that you get entangled pair, and then you decide where to measure it, which direction. And then the relative angle between the 2 measurement, Alice and Bob, they could be anything. And that's where it becomes kind of quantum mechanically really important to recognize that you have entangled states.
And if Alice and Bob's measurements are orthogonal, then they're not.
No, the thing is that
makes no prediction.
The thing is that they make random choices, and if they look at their outcomes, they see a random outcomes with respect to how they've chosen. Only when they keep a record when they did a measurement and then compare each other's, they will see a sine curve, which will depend on their relative angles.
Right.
That would be explained by quantum mechanical framework. Otherwise, classically, you cannot explain it because classically you don't have the entanglement.
But if the angles are 90 degrees, in other words,
it doesn't matter what are the angles. That's I say that when you compare, you had a sine curve that depends on the angle. Which angle?
It would be 0.
Well, that's only one orientation of the 2 measurements.
Oh yeah,
but then you can
for
have
any other
any
orientation,
angle.
There's a correlation. But for orthogonal measurements, there's no correlation.
Right, but the thing is that this is one specific one, and the point is that you see in your data that you actually at this specific value on your sine curve.
Right.
Yeah.
Or maybe it's a cosine curve.
Well,
Because
Either way.
90 degrees, orthogonal would be 90 degrees, cosine of 90 degrees.
It depends
is zero.
yeah. It depends what are the entangled states that exchange it.
Yeah, and to get at the point about entanglement, that, yeah, so like after this unitary, I don't know if they'll be in a maximally entangled state per se, but certainly, so like what you see here is that like when you, after this unitary, like when you project onto the different basis states of the auxiliary, it steers the system to each of the seq-popum states that correspond to it. So yeah, so like most assuredly, there's entanglement, whether it's maximal or not. I guess so. I'll look into that. So yeah.
So the philosophical portion, does it get into what is the meaning of life? Or is that a different meetup?
Yeah, in a way. Okay, so yeah, what is the philosophy here? You know, what the Cubists are trying to do, and we won't dwell too much on this because it is already somewhat late, I suppose, and the sun has set. But worth talking about it for a little bit, since we've come all this way. So like I was alluding to before, like there's lots of different like ways of thinking about probability theory. Dave Finetti was like a famous probabilist who famously was like, probabilities don't exist, right? People are always talking about, oh, I'm trying to figure out what's like this unknown probability distribution. And he's like, no, probabilities aren't like objective features of the world. They're, representations of beliefs. And what you really should think about when you think about probabilities is sort of the process of updating them. Like not so much that there's like one right answer and you're just trying to get closer to that, but that, there's like a process whereby you update your beliefs. And then the idea is that probability theory gives you, basically consistency criteria, coherence. Like, well, if I believe this and I believe that, then like if I assign this probability to that, then that would be inconsistent in the sense that someone could make a buck off me. In other words, there's this idea of Dutch book coherence. So, you're sort of like making things operational by thinking about like betting on things on the basis of your probabilities. And the idea is you want to assign probabilities in such a way that nobody can like always make money off of you because of your like dumb probability assignments, okay? So that's the idea. It's like probability theory is about consistency, right? It's like, it's not like a physical theory. It's just sort of like a normative theory. It's saying like, if you don't want to lose money, then you should gamble this way. Like, given, your different probability assignments, how can we sort of, bet consistently on the basis of them? And so, probabilities are, are seen in this view as being subjective, epistemic, relating to, the knowledge or the beliefs of somebody, an agent who's interested in gambling, whatever that may be. And so, the Cubists, like, as I say, they sort of have this, you read their papers and, they're like these sort of two tracks to their research program. One is sort of mathematical and based on the, the stuff that we've already talked about. And then they try to draw these, philosophical conclusions from it. And again, it's like, you can take it or leave it. But there's some interesting features. And certainly, like, you look at the literature, over the last 20, 25 years, it's like in defending the position that quantum states are epistemic, it's caused controversy. It's caused like lots of commentary. It's forced people to divide themselves into different camps and all that. I think it's led to a kind of a productive discussion about things. So, that's the idea here, that quantum states are not, ontic. They're not ontological. It's not like, right. And that'll vary from interpretation to interpretation, right? Like maybe depending on your version of Bohmian mechanics, it's like, if you like think about in terms of the pilot wave, you're like, that pilot wave is like real. It's like a real wave, that like really exists. Quantum state is just this pilot wave. Or, many worlds is like, there's this, objective quantum state that like describes like the multiverse, okay, or whatever. The idea is that, what the quantum state does is like represent reality. And the Cubists, are like, maybe quantum states are actually just like in your head, they're epistemic, they're tools that you use, ways of organizing your beliefs about quantum systems. So they believe that there's quantum systems. They just think states are subjective. They represent your beliefs about those quantum systems.
So Matt, can I ask a philosophical question?
Mhm.
I heard a brilliant physicist named Leonard Susskind say that he doesn't understand the difference between probability and statistics. Now, of course, you know what my feelings are, and I think if he doesn't, he better go back to school.
Mhm.
If you're a Bohmian, the difference is that probability is not deterministic, whereas you can have an actual statistical distribution of initial conditions, which is real. I mean, if you have a container of gas, there's a statistical distribution, an actual, or in the case of Bohmian mechanics, the belief is that there's a statistical distribution of actual initial conditions. We just don't know how to measure them or figure them out, as opposed to probabilistic outcomes. So what is your view on that? And do you believe that you don't understand the difference between probability and statistics like Leonard Susskind claims?
I know what you're saying, right? So it's, it's a question about like, I wouldn't contrast it like probability versus statistics, but like the question of the, sort of status of both probability and statistics in a deterministic versus an indeterministic world, right? Like you're saying, even in a deterministic world, a Bohmian kind of interpretation of quantum mechanics, there's still statistics. You can still apply probabilities and use them to reason and so forth, but they relate to your ignorance. In deterministic theories, particularly Qbism, and again, I like a lot of different theories. Like I wake up in the morning, I'm like, today feels like a many worlds day. Like today feels like a Cubist day. Today feels like a boat. I go back and forth, but like, just, what the Cubists think is that, yes, the world is indeterministic. Totally. It's like, it's, so yeah. So like, they believe both that the quantum states are subjective in the sense of representing your subjective beliefs about a quantum system. Although it doesn't commit them to a completely like subjective view of like reality. For example, it's an objective fact that, when you're betting on quantum systems, you should use the quantum formula, like the Born rule or whatever, seen as like an addition to probability theory in the sense of like another consistency criterion, another coherence criterion for making sure that your different gambles or bets are consistent with each other. And when you look at that formula, it's like, you notice that the dimension of the Hilbert space plays like a special role. So that like they would say, like the dimension of a Hilbert space is something objective, even if the states that you assign to it are, subjective.
See, now my view, and I think most Bohmians would agree, is that in quantum physics, probability implies non-determinism, whereas statistical distribution implies determinism. I think that's the key difference. And I know you and I have a different attitude towards that.
I don't, I don't think that is like, if you want to use those words that way, like that's perfectly fine. I don't know if that's like the standard way of contrasting it. Like that probability implies indeterminism, statistics implies determinism.
Well, I mean, in the,
Yeah, there is a
you know,
real distinction, for sure.
Copenhagen
I agree
versus
with you.
Bohm, that's essentially the difference.
Let me share with you one issue that I have with Bohm, which is the following. Bohm sounds like a classical deterministic theory. You have an equation of motion that looks almost Newtonian, and the trajectory of a particle is completely determined. There's nothing probabilistic about it. The point is that at the core of Bohmian mechanics, you have the guiding wave. Now, when I look at a car in the street, I can test simultaneously each and every point in the car simply by seeing it. Every point of the car that I see it because some photons are being reflected off this point and I detect those photons. So I know pretty much everything I could possibly want to know about the car, all the tiny little details about the car, it is there, it is real. Now, it is the exact opposite with the guiding wave. The guiding wave is not something that we can detect. Suppose you have an electron going through two slits, you do a two-slit experiment, and I'm not even going to bother to detect where the electron ends up. I don't really care about the trajectory of the electron. The only thing I do care about is the guiding wave. I want to see it. I want to test it. Can I test the guiding wave? Can I see the guiding wave? No, I cannot even see one single point of the guiding wave, except if I detect where the electron has hit the screen, then okay, now I have detected one point of the guiding wave which fills the entire space. So at most, I can detect only one point out of a guiding wave that fills the entire space. And the guiding wave in and of itself is completely undetectable, non-measurable. And
I'm sorry.
so, yes, on the one hand, Bohmian mechanics does give you the impression that you are dealing with a complete classical theory, but I don't know of any classical theory where the essence is not measurable. Again, let me present another example with classical physics. In classical physics, the trajectory of a particle in a gravitational field is determined by the gravitational field. The gravitational field determines completely the trajectory of a particle. If I kick a soccer ball, the gravitational field of the Earth is going to determine exactly, completely the trajectory of the soccer ball. But in classical physics, I can also measure the gravitational field even without a soccer ball. I can measure the gravitational field at every single point in the universe and get a number and get it completely with absolute precision. It is real. It is the gravitational field is something real in the sense that it is observable, measurable, whereas the guiding wave is not at all measurable, not at all observable. So,
Moshe, can I answer that? I agree in large part with what you're saying, but you're leaving out a very critical point, a very critical conclusion in Bohmian mechanics, and that is that the trajectories are not static. They are dynamic. And by the way, Bohmian mechanics predicts entanglement. There is entanglement between the parts of the system. That is predicted by Bohmian mechanics, namely the quantum potential, whereas
the trajectories are dynamic in Bohmian mechanics. This means that the guiding wave is dynamic.
That's what I said.
The guiding wave is not static. It is dynamic.
Yes.
It's not observable.
Well, depending on what you mean by observable.
I cannot take a
Yeah, in the
picture of
classical
the guiding
If
wave.
you take a picture, you throw a ball up in the air and you take a snapshot at an instant of time, you're only getting one position. Does that mean you know the entire trajectory?
This is because I'm doing a very simplistic experiment. In principle, I
Yeah.
can measure the gravitational potential at every point in space. If I just throw a soccer ball, I don't measure in every point in space. But I can take a little measurement device and measure the gravitational field at every point in space. I can do it. It is
Okay, but let me
To be
just finish
fair,
my.
I mean, to actually execute that, I mean, you'd have to.
I agree with that. But
formulate it in
let me
terms of
can I
its
finish
effect.
my point?
I
Let
mean,
me finish my point. Bohm's mechanics predicts entanglement. Through the quantum potential, the system is the components of the system are entirely
Well, so is your point
entangled.
that it was like never class, like we should
Can I
think
finish
about
the
it in a
point?
classical way?
It's akin to classical, but except for the entanglement aspect, which Bohm's theory predicts, whereas entanglement is inserted by hand in Copenhagen.
Oh,
Copenhagen doesn't predict entanglement.
that's a bit of a
Of course it does.
ridiculous.
Well, only in a very roundabout way, through the EPR.
No.
That's ridiculous. I mean, it's the same entanglement in both theories. I mean,
Conservation of angular momentum. If you have conservation of angular momentum, you have entanglement. End of story.
and
Really?
in both cases, when you're describing,
I don't think that's what Bohr believed.
I mean, when you formulate the guiding wave or whatever, I mean, you use like the tensor product, like just like normal quantum mechanics.
But the point is the guiding wave or the trajectories, whatever you want to call it, come from the quantum potential, which indicates entanglement among all components of the system. And that guiding wave is changing dynamically and instantaneously.
All true.
It's non-local. It's a non-local phenomenon. And Copenhagen only predicts that it doesn't predict it at first, but the EPR paper, which Einstein predicted entanglement with the EPR paper, but he didn't believe it anyway.
Okay, well,
Because he didn't see any physical consequences. But Bohm shows you where entanglement gives you the physical evolution of the system. Through the quantum potential, which Copenhagen does not come up with in any way.
I think that's like a little bit of a false choice. I mean, there's like entanglement in both in all interpretations.
Well, there is. I mean, entanglement is empirically verified. Certainly, there is such a thing as entanglement.
Well, so maybe I should skip forward a little bit to. I mean, because we could talk about how like the Cubists like think about like entanglement and so forth in a local way. But I mean, again, I mean, it's like, everything you say about Bohm mechanics is true. The question comes down to, do you want to interpret entanglement as like a instantaneous, like non-local force between things?
That's what it is.
Or do you want to interpret it in a different way? I mean,
no, but empirically.
Other ways to interpret it.
Empirically, and Einstein didn't know this because he was already dead. But Clauser and Aspect and other
so Einstein
experimentalists empirically verified entanglement. Experimentally.
That's not the issue. There are other interpretations.
But we know entanglement is non-local. You can't say it's local. It's non-local. We know that.
Go ahead.
You can say it's local, relative to different theories, right? Like the classic example in many worlds is that, it's like you find yourself in like a branch of the wave function. And so of course, when you go look at the other entangled particle, it's correlated.
Not verified empirically.
But it has the same status as the Bohmian thing, like literally the exact same status. It's like, it's just a different explanation. It's instead of positing that there's a non-local force, you posit that there's, several quote unquote worlds. And of course, you experience the one that,
Well, that's called science fiction. It's not called physics.
And on that point though, I mean, it's like, if you look at Einstein, like what Einstein was saying in that paper, like one of his like most fundamental assumptions was that, different parts of space, like separated things, have autonomy. Like, there's no implication there of free will, but like Einstein's most basic assumption is that like we even like know that there are like two things because they're in different places of space, and that means that they should be independent of each other. So Einstein would have been horrified by Bohmian mechanics.
And Einstein went to his grave believing in locality. He didn't believe his own discovery in the EPR paper of entanglement, which he predicted but never believed in. Einstein died in what, 1954? Entanglement was not empirically verified experimentally until a decade later by Clauser and then Aspect two decades later.
I've emphasized this distinction before. So when we say non-local, we can mean two completely different things. On the one hand, we can mean that there's like a non-local, like action at a distance force, okay? And then on the other hand, we can be like, when people like measure, correlations between things that may have been space-like separated, we find, again, like that they're correlated. And we can explain that correlation without like any idea that there was an interaction like that caused that to happen. Okay, so like through interaction, things may get entangled and then they have these non-separable states or whatever. But, in like Qbism, in many worlds, and like many of the other theories, they don't look at that entanglement as the result of like a non-local force. Like, the way Bohmian mechanics works, yeah, it's like totally. It's like, in order to explain the correlations of entanglement, you have to posit that like the little particle is just basically like telepathically communicating.
But
like,
Matt, I'm not talking about alternative theories. I'm talking about empirical evidence that proves that entanglement is non-local. Empirical evidence, which is evidence that Einstein did not have, let alone Niels Bohr. But we now know that it is physical reality because of Clauser's experiments.
Again, you're not really.
It's not a theory.
Like,
we're talking about empirical evidence. So you can't. Once you've established that entanglement is non-local, you can't say I have a theory that it's local. It doesn't jive with the empirical evidence that we now have.
You absolutely can. What you give up instead of locality is realism. The idea that the outcomes to measurements pre-exist.
Yeah, like I said, we're talking science fiction now. We're not talking science.
Fiction. Again, you have a preference for like objective, realistic, deterministic theories. A, not all of us share that preference. B, all of these different interpretations like explain the same experiments in equally good ways.
Well, entanglement is certainly deterministic. Even if you don't believe in determinism, entanglement is deterministic. There's no way around that.
So let's go on to like, how does, for example, Qbism treat, this issue of entanglement? So, this will clarify like what we mean, like in what sense can we think about this like locally? So in addition to saying that like the quantum states as such are subjective in the sense of representing the beliefs of agents, about quantum systems, Cubists also hold that the very outcomes of measurements themselves are subjective, not in the sense of being vacuously open to interpretation, but in the sense that they are experiences, somebody's or something's experience. And it's precisely these subjective experiences that are being gambled upon. In other words, we should look at quantum mechanics like probability theory. It's not a theory of the objective physical world. Like, it allows us to organize our statements about the physical world. But as such, it's a sort of first-person theory by which one may predict the future consequences of one's actions in experience. So for example, you think about the dilemma of Wigner's friend, okay? So this is from, one of Fuchs's papers. For the Cubists, like the real world, the one both agents, Wigner and his friend, are embedded in with its objects and events are taken for granted. What is not taken for granted is each agent's access to the parts of it he has not touched. Okay, so this gets at this idea of like, when you say like, you give up realism, I mean, that sounds crazy, right? But like, it's not really that crazy if you're saying something that like, you have to appeal to the actual experience of people like doing stuff. And you can't assume that there's like a God's eye point of view from which like everything is just like objectively inspectable.
So can I ask a question?
Well, let me just get through this little paragraph.
Does
No,
this theory,
Michael, stop. Let Matthew finish.
he may be able to answer this.
Don't interrupt, Michael.
Jesus Christ.
Don't interrupt, Michael.
Yeah, just
We're,
one second.
Moshe, we're all interrupting. Come on.
I mean,
Stop
is it really a quick question? I mean, whatever.
A quick question.
Okay, fine.
Does this predate consciousness? What happens if you don't have an observer? Did the universe not exist? Or does this, whose observation are we talking about prior to conscious beings?
Right, so Qbism is a theory of experience. It assumes and takes for granted experience first.
Whose experience?
Experience. Like, in other words, it's an attempt to, in general, ground philosophy on your experience. You can, the Qbism as such, like, doesn't answer that question. And it doesn't need to.
But how do we interpret physics prior to sentient beings who had consciousness?
I think that the question is deviating too much, and you're preventing him from really trying to explain what he was planning to do.
Okay, I apologize.
Okay. I mean, okay, well, all right. So this is the Cubist reading of like the Wigner's friend thing. Okay, so what's not taken for granted from the Cubist point of view is that each agent has access to the parts that he or she has not touched. So in other words, in this experiment, Wigner's over here and his friend measures the spin and they get, from Wigner's perspective, entangled or whatever. So at that moment, Wigner is holding like two thoughts in his head. A, that his friend interacted with a quantum system, eliciting some consequences for the interaction for himself. And after the specified time, for any of Wigner's own future interactions with his friend or the system or both, he ought to gamble upon their consequences according to this, which is to say, rho describes the friend, psi is the spin, say, and u is this entangling operation. Okay? So one statement refers to the friend's potential experiences. The friend had an experience, a subjective experience of getting an outcome, all right? But as far as Wigner is concerned, when he perfectly can like allow in this picture that his like friend had that experience and Wigner has no access to it. Like Wigner is not his friend, like whatever. He can't just like magically know what the friend experienced. So he can accept that that's true. And also that like when he himself wants to gamble on his future interactions, with either the spin or his friend or both, he should treat the spin and the friend as being entangled. And so, this gets at the key thing, right? So like in like an ontological interpretation of the quantum states, like this is paradoxical, right? You're like, well, what do you mean? Like, if the quantum state's real, then it's like, from, Wigner would say, oh, the friend and the spin are entangled, but like, that means like there was no actual measurement outcome. But then like the friend would have had to say, no, like, the quantum state of the spin is collapsed or whatever. And so the Cubists are like, the error in thinking here is in pretending that quantum states are ontological, that they like represent reality. Instead, quantum states are to be seen as like probability assignments, as being these like subjective sets of beliefs that we use to, gamble on the future. And there's no contradiction, if you don't take for granted that an agent has access, as I say, to parts of reality that he has not touched, that like Wigner can think, okay, like my friend has had this subjective experience, it was up or down, whatever, that's nice for him. But as far as I'm concerned, as far as my experience is concerned, I have to gamble like on this entangled state. Indeed, like precisely because like what is even, you know, from this point of view, the use of the entanglement, it's like a way of like representing correlations between two systems while being completely agnostic about like what are the actual values. So, you know, Fuchs says like the world is filled with all the same things that it was, you know, before quantum theory came along. Like each of our experiences, that rock and that tree and all the other things under the sun. It's just that quantum theory provides a calculus for gambling on each agent's experiences. It doesn't give anything other than that. It certainly doesn't give one agent the ability to conceptually pierce the other agent's personal experience. It's certainly true that with enough effort, Wigner could, you know, apply the reverse unitary and like disentangle his friend in the spin, which would cause his friend to have, you know, then he would predict that his friend would have amnesia, okay? And he wouldn't remember what result that he got. But then Fuchs says, well, we already knew Wigner could do that. Just hit him on the head with a mallet and he'll forget. So, you know, the point here is that when we say quantum states are subjective and then like even that the results of measurement are like subjective, this is not like solipsism, okay? Like it just means that, you know, these things refer to, on the one hand, personal beliefs, and on the other hand, like experiences. And the idea like is that, you know, unlike in a sort of a classical world, it's like there's no sort of God's eye perspective from which, you know, all the experiences of all the different agents are just like open to view. And that's the sense in which they mean subjective. And moreover, it's not like you can just, you know, willy-nilly believe any old thing is true, in the sense that, you know, by this sort of very nature of it, like the actual results of measurement are like precisely like not within the control of the person making the measurement, so that they, you know, in some sense conceptually divide the world into subject and object, and the, you know, subject has the autonomy to set the experiment, the object has the autonomy to respond to the experiment. And then here, this is like sort of like one of the sort of recurring ideas in Cubist thought, that the act of measurement itself is a kind of creation, a mutual experience that transcends the very distinction between subject and object, a linkage between oneself and the other. And to quote Fuchs and Stacy, quote, Qbism says that when an agent reaches out and touches a quantum system, when he performs a quantum measurement, this process gives rise to birth in a nearly literal sense. So, you know, the only real conflict here, you know, philosophically, is the notion that like the only valid physical theories are those that attempt to directly represent the universe in its totality as a pre-existing static system, an unchanging monistic something that just is, okay? Qbism presents a sort of vision of the world which is in a constant process of being created, that in some fundamental sense it's unfinished, and that this is like the best way of thinking about the meaning of quantum indeterminism. As such, you know, like when you think about like the interconnections, like other parts of science, you know, from psychology to neuroscience, like whatever, problems about the human mind and experience and all sorts of things, you know, one thing that's interesting about Qbism then is that it sort of clears a space for what Fuchs would refer to as like real particularity, or, you know, interiority in the world. In other words, for Wigner, you know, considering his friend and the spin, you know, with his back turned, that phenomenon has an inside, so to speak, a vitality that he takes no part in until he, you know, himself interacts with one or both relevant pieces. So, you know, often in interpretations of quantum mechanics, you know, one tries to achieve objectivity by focusing, like, and this was like, you know, the track taken by Niels Bohr, and, you know, and in some sense is very different from the Cubist approach. You know, they would focus on like the big bulky apparatuses that you use to actually perform quantum experiments, you know, especially in the old days. And the objective records of outcomes left behind by these machines. But the Cubists take a different track. So they even, go back to an analogy by Bohr, although they use it in a kind of a different way than him. He considers the analogy of a blind man seeing with a stick. Like he's not like actively, rationally, like thinking about the stick and how it's skittering off this and that, and like analytically, like reconstructing whatever. Rather, for this guy holding the stick becomes an extension of his body. In other words, he sees with the stick. And so with that, like these are, this Fuchs sort of sums up the three tenets of Qbism this way. One, quantum theory is normative, not descriptive, right? It's a way of, it's like saying, this is what you ought to do. When you like assign probabilities to events, you ought to be consistent. And we need to, sort of enlarge normal probability by adding another consistency criterion, which amounts to the Born rule. And that's what we've seen today, basically. And of course, this is not to say that it's like, you don't do like normal physics. It's just to say that like the normal physics, like, oh, this thing is spherically symmetric. Like, oh, this thing is like, okay, whatever. Like those are the priors like that you're bringing to the situation, and they may like be useful in describing what happens. But the idea that like quantum theory as such, right, in its bare outlines, insofar as it's like they're looking at it as an extension of probability theory, in the same sense, it's normative, not descriptive. Second, my probabilities cannot tell nature what to do. In other words, it's sort of like suggesting that, the difficulty with other interpretations of quantum physics is their tendency to like reify or objectify the quantum state and treat it as like a representation of what's really there, And three, a measuring device is literally an extension of the agent. And so, in this sense, it makes, and so that's the way to sort of understand this idea of like, I make a measurement and I get like a certain outcome, which is like an experience. Like, by using the apparatus in some sense, they're like my hands, like my eyes. And like you can sort of interpret in this point of view, entanglement and the use of the tensor product as relating to the objective fact that we require a way of representing, correlations while being completely agnostic about what is correlated, insofar as we haven't reached out and touched that thing and actually, in a sense, elicited one of these acts of creation. So, in this sense, like I was saying, you can look at Qbism as like a local theory. An experimenter has like two entangled spins, they make a measurement, and they have an experience. And, the textbook would say, or like, your Copenhagen textbook would say, oh, the state of the other spin, like immediately, quote unquote, collapses. Cubists are like, all right, so the quantum theory allows the experimenter to predict, they like, if they go over and measure the other spin in the same direction, they'll have another experience of the answers being correlated. But what they specifically deny is that like, just because quantum theory assigns probability 1 to that outcome, that means that that thing was, say, like up as a property. Because remember, for Cubists, the quantum states are epistemic. They represent beliefs, okay? So that like, it does, to say probability 1, which by the way, goes back to like the EPR paper where, Einstein and others try to define, an element of physical reality by saying like, if without any way disturbing the system, we can assign a probability 1, et cetera, et cetera, et cetera. There's a pre-existing element of reality. So, their point is that, probability 1 subjectively just means you're willing to bet an infinite amount of money on it, and like and the point is that if the experimenter never goes to actually like check out that other particle, it's yet another unperformed measurement, an unperformed experiment. And insofar as they look at, experiments as acts of creation, that, like outcome doesn't even exist yet. And so they point out that, like whenever you actually cash out on like what entanglement means, you have to compare, right? It's like, okay, two things are entangled. Like, how do you know? Like you measure the one and then you gotta like go over to the other guy and measure him. So in some sense, in order to confirm that there was entanglement, something had to pass between here and there. And so actually, the Cubists quite approvingly cite Einstein's EPR paper, you know, what they give up, unlike the Bohmians, is not locality. Instead, they basically give up
What's up the
objective
middle, man?
realism. So, you know, I would say, you know, that, you know, what makes Qbism kind of interesting is like this attempt to sort of give nature as much latitude as possible. You know, usually in science, you know, we're mentally trying to constrain nature, applying concepts, laws, systems, etc. And that's fine. But, you know, Qbism proposes that in some sense we live in an unfinished world whose creation is ongoing and ceaseless, and this profound open-endedness is the real meaning behind quantum. Indeterminism, you know, you don't even have to think of the universe as being governed by immutable laws and additional conditions fixed from the beginning. Rather, new situations are, you know, coming into being all the time. And it's not to deny that like there's regularities and symmetries and so forth. Evolution proceeds apace, you know, there's the law of large numbers, etc. Like none of that is to conflict with the obvious success. You know, there's patterns, of course. But the idea is to take seriously, you know, what John Wheeler would have called like the participatory universe, that, you know, we and everything else are constantly engaged in bringing the universe into being in some sense together. And then, you know, these are some quotes from Wheeler's, you know, famous paper from back in the day, you know, law without law. Like it's difficult to see what else other than that, law without law can be the plan for physics. For him, it's preposterous to think of the laws of physics as installed by a Swiss watchmaker to endure from everlasting to everlasting. But we know the universe began with the Big Bang. In other words, he's saying the laws must have come into being like everything else, you know? And so, you know, how can we understand a world in which like even the laws themselves have an origin, have a birth? And he is sort of like, hey, you know, maybe like the way that we should conceptually think about this is that the very act of what he would call observer participancy are the sort of fundamental building blocks of creation. So there, then you know, he has a sort of cute exchange. I think this was back in the 70s, maybe. You know, it's like he's asking, you know, do elementary acts of observer participancy, do they serve as a kind of, you know, some sense an ontology for the world, you know, as opposed to particles, fields, etc. And I believe the story is that the guy who asked this question was actually like a priest or something. He was like, Dr. Wheeler, who was there to observe the universe when it started? Were we there? Or does it only start with observation? Is the Big Bang here? And Wheeler says, a lovely way to put it. Is the Big Bang here? I can imagine that we will someday have to answer the question with a yes. In other words, that mechanism by which the universe is brought into being is all around us. It's actually ubiquitous. And, you know, the one thing I think I can see a value in like another sense of a lot of this stuff is that this sort of clears a little bit of like ontological space for like the quantum systems themselves, right? Like if you're just sort of working in an ontological interpretation of the quantum states, you know, again and again, you have to ask yourself like, well, how does like this property, like if I'm imagining the quantum state of me, right? It's like, how do my mental states like supervene on like my quantum states, like et cetera, et cetera, et cetera. And, you know, obviously, you know, there's like a, you know, you look at my brain, you can, yeah, predict like what I'm going to do. But I think that it gets at like this sort of interesting question. If you look at the quantum states themselves as like being non-representational, as like having to do with like beliefs, then it clears ontological space for the quantum systems to be like made of who knows what other stuff, qualitative, perhaps experiential stuff. And so I think is like relevant, you know, to, you know, issues in you know, questions about like the philosophy of, like we've already said, you know, consciousness and mentality and perception and so forth, where, you know, philosophers confront the question about qualia, like what are the nature of our sort of qualitative, subjective experiences and so forth. So, Fuchs says, Qbism means that reality differs from one agent to another, but this is not as strange as it sounds. What is real for an agent rests entirely on what the agent experiences, and different agents have different experiences. An agent-dependent reality is constrained by the fact that different agents can communicate their experience to each other, for sure, limited only by the extent that personal experience can be expressed in ordinary language. In this way, a common body of reality can be constructed, limited only by the inability of language to represent the full flavor, the qualia of personal experience. And so this is what I mean by in some sense, cutting the Gordian knot of a lot of sort of paradoxes that come in when you're considering, the relationship between mind and matter, like whatever you want to call it. That it might make sense to start from like an experience first theory, that like you take for granted, what is directly closest to us, indeed, like our actual experience. And it's very interesting, like insofar as these guys, go back and like draw on the work of these philosophers, from like the late 19th, early 20th century, like even before the birth of quantum mechanics, and perhaps even more interesting insofar as that they, were writing at a time when, classical physics like reigned supreme, and, physics as such would have said like, for sure, world's deterministic, et cetera, et cetera. They were even then, advocating like a deeply kind of indeterministic picture of the world, and an experience first one, like as opposed to what they would have termed like rationalist theories, which in their mind were theories that like tried to understand the world by positing a conceptual system and then trying to derive experience from concepts, okay? And they're like, that doesn't make sense to us. We think that the experiences come first, and then we use concepts to organize our experience. But there's no way you're ever gonna like start from like some set of concepts and derive your own experience. It just doesn't work that way. And so that's how they sort of developed this sort of opposition for what they would have called like empiricism versus rationalism. I mean, the word empiricism is an interesting one in that sense, because as the 20th century wore on, I mean, that word came to mean primarily like, is there empirical verification? Like, can you write down a bunch of numbers that are the results of like big bulky apparatuses having made a bunch of measurements, etc. After especially the influence of logical positivism. But actually the meaning of the word, when James was writing, say like in like the 1906s or whatever, empiricism or radical empiricism was taken to mean a philosophy which puts subjective experience, like personal experience, at its forefront. I realize it's getting quite late. If people have to go or whatever, by all means. And now would be a good time if there's any lingering questions. For the rest of it, I was just going to read some cool quotes from William James that I thought were sort of give the flavor of what's going on. But please, if anyone has any comments.
Matthew, before we go, I would like to make a suggestion. Way back when I was a grad student, I used a lot Feynman diagrams. If I had not known about Feynman diagrams, it is very simple. I would not have been able to write my doctoral dissertation. Suppose I didn't know about Feynman diagrams, I would be stuck. And suppose that at that point, someone would come to me and tell me, hey, look at this, Feynman diagrams, neat stuff. And he would tell me, but there is a patent on it. If you want to use those, you have to pay lots of money. I would have paid whatever it takes to get these Feynman diagrams. For me, it was vital. The benefit of Feynman diagrams was more than obvious. It was a necessity. Now, I'm asking myself a similar question about what we heard today about Qbism. Now that I have heard about Qbism, what are the benefits that I can derive from Qbism? I know what kind of benefits I can derive from Feynman diagrams. For me, they have been existential. Now, let me make a suggestion, Matthew. If you want, it is up to you. There's no necessity, but if you want, maybe you can think of some explicit, concrete example where here is someone, a physicist, an experimentalist in the laboratory, running an experiment, and very detailed, very concrete. This is the apparatus that this guy is using. This is how he's doing his measurements, and so on and so forth. What would he be doing different if he knows about Qbism than if he didn't know about Qbism? What would be the benefit to this guy? Just a suggestion, something that
Yeah, for sure. And it's very in the spirit of the, pragmatist point of view. Yeah. Like if you're making a distinction, what are the consequences? What does it matter? And I mean, just to say like, something about it, like I would say that, again, like whether you buy this philosophical interpretation, you can use seek problems to do quantum tomography. It might help you in various aspects of your work in the lab or in quantum information theory. In terms of, sort of like if, like I would say, like if you're a person, like a philosopher who's just tortured by the question about realism versus determinism versus like, is it even coherent to think about a world that's unfinished? Is that just like nonsense or whatever? Like if that, bothers you, then like that, this can help. I think finally that like, I quote this part of one of the papers where they're like, the burning question for the Qubist is how to model in Hilbert space terms the common sorts of measurements we perform just by opening our eyes, cupping our ears, and extending our fingers. And I think for me, that's like, when I was reading about Qbism, I thought like two things. Like one, I thought, okay, I feel like I've learned something new about quantum mechanics. Like I never suspected that you could formulate it in a way that made it look so similar to normal probability theory, just this slight deformation to the law of total probability, etc. Like I feel like I understand more about the structure of quantum theory just by having, gone through that. But, at the same time, Qbism also pretends to be a theory of experience, of belief and experience and so forth. But, reading the papers, like I'm honestly not sure that I've learned something new about experience. Like in other words, at their suggestion, the last couple of weeks, I've been reading a lot of William James. He's a psychologist and he's a beautiful writer. I mean, it's like the joke that everyone tells is like, Henry James, the novelist, was his brother, and Henry James was a novelist who wrote like a psychologist, and William James was a psychologist who wrote like a novelist. And one of the things that makes James's writing interesting is that it's he proposes theories and goes over experiments, in the early days of psychology and so forth. But like one of the things that's really distinctive about him is like the way that he captures kind of like the flow and unfolding of thinking and perception and experience and stuff in the course of his writing. So that like if his sentences had been like less, perfect, like you wouldn't even know what he was talking about. But he's able to kind of like trigger even like the experience he's talking about in you because he's such a good writer. And so you reading him, you like have this feeling like, yeah, like I understand something about my experience in like a kind of psychological way that like I didn't think about before. I'm not so sure I get that feeling from Qbism itself. I mean, obviously it's a theory developed by physicists, so I don't know what I was expecting. But I mean, just like, psychologists spend all day thinking about, the structure of the mind. And so it seems to me that, for Qbism to really prove itself, like not just as a sort of reading of the quantum mechanical like framework, but also as like a theory of experience, it's going to have to make like sort of novel predictions, not just on the quantum side, but also on the side of everyday perceptions and something that can like help us to better understand the nature and structure of our subjective experiences. That, I think, if they could do that, would, elevate this theory, into prominence, because you would be able to say like, hey, look, the Cubists are saying, this kind of interesting thing about experience. I mean, what would the many worlds people say? What would the Bohemian people say? What would the Copenhagenists say? Can they make a similar kind of account? And it seems to me that, these guys sort of recognize this insofar as, they're saying this kind of thing. Like, how can we model in Hilbert's-based terms, even just the everyday kinds of acts of experience and perception that we all rely upon?
You have to admit, I did not quite follow all the details of today's presentation, but something that you said that bothers me a little bit is that apparently this provides some sort of a classical view of quantum mechanics. And it is not clear to me that the two can possibly be consistent.
Yeah, it's not a classical view of quantum mechanics. It's just saying that you can like the 10-second version is, you can rewrite the Born's rule as a deformation of the law of total probability if you use seek problems. So
to me, what makes quantum mechanics quantum mechanical is a combination of the Born rule and the superposition principle. If you have two valid eigenstates, any linear combination of those that's normalized is also going to be a quantum state. And when you use the Born rule to compute probabilities, you will get interference. This interference is strictly quantum mechanical. You don't have anything remotely resembling this interference in classical mechanics.
for sure. So that, what you just said, is summed up in the second formula here. So that, like, if you consider the first formula, remember what happens. Like, we've done a Pavem measurement, okay, and then the states collapsed, and now we have, like, if you're just thinking about in the usual terms, a density matrix, which is just a statistical mixture of the outcome states weighted by the probabilities. So that all the quantum coherence is gone. So in order to describe the quantum case, it's like, yeah, we need to take into account superposition, coherence, etc. And that's what this second formula does. But it doesn't do it by, talking about probability amplitudes and complex vectors. Instead, it's rewritten in the language that makes it look as close to normal probability theory as possible, where you have the same sort of prior probabilities, the same conditional probabilities. But you think about, like, what is this sort of deformation, do? It sort of rescales that, it kind of subtracts off this bit. And especially when you look at the other formula,
When you use this Qbism formula that you just went over for the double slit experiment, do you get the interference pattern?
Yeah, for sure. That's exactly, yes. Yeah, totally. So yeah, so you could look at it like, you have like a particle, you could do a Pavem or not, and then you could, do a position measurement or whatever, and that would be your von Neumann, okay? And so like what this second formula is exactly taking account of is the existence of the interference and the superposition. And so, but it's expressed like, without the amplitudes, without the complex numbers, totally in terms of these probabilities and conditional probabilities. And you can see, like, in this version of it, where we're considering a Pavem measurement on the ground, it's like, you can see that it's like in a way that's different from normal, like the different sort of parts of the probability vector and the conditional probability vector kind of like mix a little bit in a way that, wouldn't make sense classically.
You know, Matthew, I'm a very old-fashioned kind of a guy. To me, quantum mechanics starts with Schrodinger's equation. You start with Schrodinger's equation, you solve it for a particular case, for a particular configuration, you get your probability amplitudes, you get your probabilities therefrom. Now, in this expression that you're looking at right now, PIs or probabilities, are those somewhat related to Schrodinger's equation? Does Schrodinger equation play any role in here?
Oh yeah, no, for sure, right? So over here, I talked about how to describe, the time evolution. So again, the PIs, like those probabilities, right, are like specifically the probabilities with reference to this Qbism measurement, and they provide a complete representation of the quantum state. So, you can use them instead of your amplitudes. But, you're perfectly right in saying like, hey, where's like the Schrodinger equation and so forth? Like, we assumed when we were talking before, like that we already had some quantum state rho, or whatever that we cared about. And then we just sort of describe it in terms of the probabilities. But, we can also, so describe time evolution in this picture, right? So it's like, the Schrodinger equation like amounts to like there being some unitary evolution on the density matrix, right? And so you can, like, as I say, create this matrix of conditional probabilities where we're just looking at like the overlap between the Qbism projectors and the time evolved Qbism projectors. So this is sort of saying like, this is the conditional probability that we started in a given Qbism state, and then we did some time evolution, and then what's the probability given that we started in that state that we end in this particular Qbism state. So this is a conditional probability for, the Qbism state J after time evolution, given that we started with a Qbism state I. And so this stochastic matrix of conditional probabilities characterizes the time evolution like just as well as the unitary operator itself. And then, we can use it in this way, so that like if we have the original probabilities for the system on the different Qbism elements, and we have this stochastic matrix of conditional probabilities, then we can get the probabilities at a later time in this way. And again, like what the Cubists like about this is that the classical formula for stochastic evolution would be this, where you would use the stochastic matrix in one way, and then in just a quite analogous way, we instead employ in a different way. And so if you think about it, it's like, so recall, like in the case of measurement, we were talking about it like we would use this type of formula when we actually did an intermediate measurement and then did another measurement. And then we'd use this type of formula if we didn't, if we went like directly to the von Neumann thing. And so what this is saying is that we have to treat, so again, this unitary matrix, like this stochastic matrix of conditional probabilities, same in both cases, but here it's like we're considering the time evolution as coherent. In other words, it's like explicitly like, we're not doing any measurements in the course of the time evolution. And so we have to use this sort of deformed rule. Like this would be the normal rule for time evolution and like, statistical theory. And, you wouldn't get like interference. You wouldn't get a coherent quantum evolution. Just up deform things like this way, then you would. So, you can.
I'm not sure about that because my concern is the following.
Okay.
Basically, these are mathematical expressions, and they're used to model systems and see how well your understanding of the system could fit the mathematical model. In this respect, I mean, shunt up and calculate is the best kind of strategy to see what you have. Then you can try to do interpretations. And when you do different interpretations, basically there would be different interpretation of different mathematical expression, or not different, there will be practically the same mathematical expressions. But then the question is, how do you understand and relate these terms and elements in the mathematical expression to observations? And to me, basically, I mean, any interpretation of quantum mechanics would be able to put eventually something and to say something about these expressions. So I don't think that pointing to the expressions, you can differentiate one interpretation from another.
No, I agree
what
with you
is
completely about that.
what is more important is, I mean, what they are subscribing to, and I see that you had, I mean, like 9 points. I mean, something that you put it after the 3 main points about the Qbism. Is that right?
Yes. Yeah, where was it? Here.
Yeah.
So this is taken from one of their papers.
Right. And again, coming from this kind of perspective of mathematics and the role of mathematics, now when you read, they do say, well, when this is kind of personal, it depends on the observer, the action, and objective, not more subjective than objective. And I think what is happening to here is they're recognizing something that's kind of it's discussed at various levels. Earlier today, somebody was mentioning about the car, and then he went to the electron. But just try to answer the question: how many electrons are in one car? My point is that classical mechanics basically is built on the premise that your observer and your observations do not interfere with the process that you're observing, and therefore it's kind of objective. So it's independent on you. But when you go to the point where you're actually trying to really do a measurement of something so small like an electron with something such big like a car, which was very often our equipment, you're affecting the system significantly. That means that you're passing beyond the classical systems, and you're getting into the systems where your measurements, observations are affecting the system. Now, of course, each observer would have their own process of observing, I mean, doing measurements, and this would cause different results. But again, putting together all the data that they collect and trying to compare with mathematical translation between one experiment and another, they would kind of eventually come up to similar set of actions and consequences and experiences. I mean, of course, my experience is different from yours because we had different timelines when we lived through different things. But if we kind of try to focus on one specific process in nature, I mean, it may be long or it may be very short and quick kind of discussions, but we would eventually come up to a point that we would understand the process, although with different points of view, but we'll start agreeing on things. I mean, we wouldn't say, well, I didn't observe it. No, I did. I mean, if it comes like this, then I think we try to figure out, I mean, what wasn't observed, what was observed, and things like this. So eventually, the consequences and actions, I mean, they will build a system of actually common for the set of agents, and this would continue growing. And basically here that they say that, well, finding a density matrix, so the actions and consequences would converge to a common set that they will agree. There could be a question about the density operator. I mean, does it have to be the same? And again, they'll find a way how to connect them. So what I'm saying is that eventually there will be a process where all these things would converge when you're studying a system. And this, to me, it's kind of start to contradict itself, because the original freedom that seems to be there, that I mean everybody can have their own thing, is kind of disappearing, and this is going along the line of multiverse and Everettian kind of interpretations, because if you just take it like this, you can say, yeah, this is similar to multiverse. I mean, everybody has their own experiences. But through the process of communication and going through, then you build entanglements with the environment. And then this is going more towards the Everettian interpretation, where you entangle so much with the environment and everybody else that you kind of come to a common understanding. And in this case, I don't know how this can bring anything new compared to other approaches.
Yeah. Yeah. I mean, I feel you. I mean, one of the first things that you said was like, considering these mathematical expressions up here. Yeah. I mean, I think from a very like practical perspective, it's like, is it useful? Like it's if you want to reformulate quantum mechanics as something like probability theory, then it's like, okay, useful for your philosophical purposes to, form this stochastic matrix or whatever, as opposed to this unitary matrix. But does that like actually help you, do your calculations? Is this like in some sense easier, or maybe it's even harder? And so, I think that, there's like a real practical concern there. Like similarly, like in the case of Bohmian mechanics, is it really worth calculating those trajectories? It's kind of computationally expensive.
Well, this is the same like doing a Feynman path integral, right? You're integrating all the paths effectively.
I think, with regard to your question of, when people study the same thing and then, they're going to converge on like a common representation of the state and so forth. And so then, like what is the use of being so whatever kind of subtle and sophisticated about like the nature of probability here? It's like, from what I understand, and I have to admit that I haven't really read the original stuff on this, but in classical probability theory, this guy Dave Finetti tried to he sort of proved a theorem that says that, like, instead of positing that there's some unknown probability distribution that you're basically trying to like approximate or learn, you can sort of get the same effect if you imagine that you're working in a situation where you're doing like a bunch of experiments and you're indifferent to swapping the experiments or exchanging them. And the theorem shows that like if a bunch of different experimenters are able to treat the different experiments that they do as basically interchangeable, and it can be shown that they're all going to like kind of converge to the same quantum or classical probability distribution. I'm sorry, someone's got their sound on.
Can I comment, Matt? Is that my television you hear in the background?
Yeah, probably.
I'm sorry. Let me shut it off and let me make a comment.
Wait, can I say one more thing first, though?
Go ahead.
So, it's just that, like, philosophically, I guess the Cubists are like invested in this idea because they want to look at reality as like under a constant process of creation, and so they want to like prevent you kind of philosophically from being like, oh, there's this thing that's like really out in the world, and we're just trying to like, that has a pre-existing reality, and so we're just trying to like, learn what that is. And so they want to like emphasize the fact that like there may not be a pre-existing thing that you're studying, even if when, lots of people do the experiments again and again and again, they converge on the same quantum state. And then the final thing I just wanted to say about that is that like, this stuff is very, like, I think that at the end of the day, like as a physicist, you use this stuff, you try to like actually, get something done. I think that like we will remain in the realm of speculation, especially with regard to things like Wigner's friend or like whatever, until we can like really, until there's like a really obvious sense in which we could like put people in entangled superposition in like a way that's like operational, right? It's like when you're considering Wigner's friend, it's just like, you know, the whole point is that, you know, subjectively Wigner's friend would have, you know, one density matrix to describe the system because it's like collapsed for him. But, you know, Wigner would have to say, oh, well, like he's just entangled with the spin or whatever. But, you know, and so that maybe gives license to, you know, epistemic interpretations of the quantum state, because here, like two different experiences where they just necessarily like differ, because this person was the one who did the measurement, whereas like this person just sort of was around while someone else did a measurement. But, you know, until we can like understand like much more about the structure of the brain, the mind, the human body, you know, and like actually start doing these kinds of, you know, whatever they would be, sort of like trans-subjective kind of experiments, right? It's like, I think that there's always going to be sort of like an open question here.
Matt, could I make a few comments? I haven't heard the whole conversation because I was called away by hunger pangs, quite honestly. But I agree with what I heard VG say about the measurement problem. In classical measurement, in all measurement, we assume that the measuring device has insignificant influence on the measurement of the state. In classical mechanics, that's possible to do. In quantum mechanics, we're using a macroscopic measuring device to measure a microscopic process. So obviously, the measuring device is going to have a huge effect on the measurement. The other thing, the whole concept here, which, you know, I object to, is that it basically precludes or it diminishes the role of objective reality. I believe in objective reality. You know, objective reality existed before sentient beings, before consciousness, and it will continue ad infinitum. The thing about the universe evolving, and I don't know if anybody is familiar with Seth Lloyd's work.
A little bit.
He's professor at MIT. But he analogizes the universe to a quantum computer in that it is continuously computing. And that's why things change. And even the laws of physics could change in that way, or have changed in that way. But we start with initial conditions, and then the computer not only, you know, computes with the data it has, but also starts computing its own new program. I guess akin to artificial intelligence in some way. And then Wigner's friend, I'm not entirely familiar with that, but it seems that Wigner wants to be outside of the system playing God. He wants to be able to observe the universe, in essence, while he's outside of the universe. You can't be outside of the universe. We don't know if there is an outside to the universe. So, of course, you have to get involved in the system. You got to be entangled with the system to make any measurements. You can't make an objective conclusion by trying to play God outside of the universe or outside of the system. End of speech.
Yeah, so I mean, I think that, yeah, I mean, there's like, you know, many points of agreement here. I mean, it's like, I think you rightly, you know, like identify the differences. So like, I would say that like, you know, a Qbist would say something like, it's like, when we talk about, you know, we are these big bulky beings with our brutal apparatuses and we're measuring this delicate electron. And so, you know, inevitably there's going to be this like reaction upon the system that's going to sort of scramble up, you know, whatever way that system was before. And so, you know, that's going to prevent us from really being able to nail down like an objective reality, because, you know, any experiment we do is going to sort of change the system, you know, under. So, but the
but there is an objective reality, unless you don't believe that.
Well, that's the question, right? So like the idea is like, you could say there was, an objective way that the electron was, in a kind of God's eye point of view, and that your attempt to measure it like disrupted it. And like, indeed, yes, of course, like that's the position taken by like Bohmian mechanics. Another route to take that, the Cubists take is to say that there was never like an underlying real outcome objective thing that pre-existed. In other words, what happens is created. Like a new thing comes into existence when a measurement is made. And it's not so much that something pre-existing was disrupted, it's more like in the act of measurement, something new is brought into the world. And so, yes, it's a fundamentally indeterministic, non-realist in that sense, that, but again, the question about like, oh, I believe there was a world before consciousness and sentient beings. It's like, it just seems to me it sort of misses the mark as far as like a criticism of this type of theory, because Qbism as such is not like posing as a theory of like the objective physical world. It's like posing as a theory that allows you to gamble on your experiences, so that it presupposes that there's experience. Like, in other words, like the pragmatists, like William James, would say something like, like our philosophical position that is that there's nothing real that's not in experience. And anything that's in experience is in some sense real.
I'm sorry, could you repeat that? Anything in experience is
Right. So
what?
Real. So like there's two sides to it. It's like, on the one hand, anything that we're going to consider to be real has to be in experience.
Well, that's cause and effect.
Well, again, it's sort of like Moshe's point, right? It's just like in Bohmian mechanics, like you're never going to experience like the wave or like whatever. It's like,
yeah, but that's a technical issue. And in Copenhagen, or any theory, in Copenhagen, there's even less credibility, because you put the Born Copenhagen relies on the Born rule, which he pulls out of his ass, quite honestly.
I think we've seen here like that you can, I mean, maybe, this funny deformation of the law of total probability is like something that, one could view as being pulled out of someone's ass. But at the same time, one thing that, strikes one about it is how simple it is. It's pretty much the simplest possible deformation that you could imagine.
But you can understand this as natural kind of answer to the question, what if I want to go beyond the von Neumann projectors and allow any kind of projectors that still have some kind of positive value, so that I can build probabilities and they don't have to be orthogonal. So then can I still build my kind of machinery to be able to answer questions? And this is actually a good thing, because earlier somebody mentioned that for them quantum mechanics starts with the Schrödinger equation, and that's kind of true in most cases, but this is basically starting with the pure state. And then when you get to states that cannot be described as pure states, then you need a density operator to describe these kind of states. And of course, the description usually is going with the von Neumann operator, projectors, because we are carrying from the pure state kind of idea of vector space and so on. And the construction, gives us one step beyond. It's a very good thing when I talk with some of my students and explaining them the block sphere. Basically, they can see immediately how the pure states on the surface of the block sphere, but then when you look at and move to the density matrix, you can see now that all points inside the sphere could also represent states of your system. And now the next step is here, because the projection operators, they are on the side of the observer. So releasing this kind of constraint to be exactly von Neumann operators and enlarging the class, you're allowing a bigger class of things. But then the question is how much, is there a formulation where you cannot go back to the von Neumann? When, for example, density operator, there is a formulation where there are specific processes in nature, quantum mechanical, that you cannot describe them with the pure states. So it forces you to use the density matrix. Is there a similar kind of situations where you cannot describe it with von Neumann projectors and density operators, and that forces you to actually use the new kind of sig problems for measurements?
Yeah, that's a good way of putting it. Like it's, it gets at this thing of like, for a von Neumann measurement, if the Hilbert space mentions D, in general, there's be like D outcomes. But for these seq problems, you have D squared. And that's like exactly the number of, matrix entries in the density matrix. And so it's like, this treats, pure states and density matrices like on an equal footing. And so, as you say, like allows you to describe like these more general processes that can happen. For sure. Yeah, and that is definitely one of the cool things about this whole way of calculating things.
Well, thanks, Matthew. That was interesting and stimulating, thinking about it. And now I learned a little bit more about Qbism.
By the way, VJ,
Yes.
what is your background?
I teach physics. So my PhD was on computational nuclear physics, especially like a few body forces in nuclei and computing the nuclear force based on CD, quantum chromodynamics, and using the Weinberg chiroperturbation theory to derive the nuclear force and describe the nuclei. But then since then, I kind of deviated, going into more like, right now, my research is mostly into astrophysics. My collaborator that I'm working with, he's the retired professor of the Geneva Observatory. We are looking into scale invariant vacuum and what this has to say about cosmology and
did you say? Wait, I didn't quite hear you. What kind of vacuum did you say?
Scale invariant vacuum theory. Yeah. It comes basically from extending the Einstein general relativity to actually use the Weyl idea of the gauge freedom, but it's specific gauge freedom that it's applicable for homogeneous in the isotropic universe. So as a result, you can actually find a solution to the equations of this extended Weyl integrable geometry, which is a little bit going beyond the Einstein, in a sense that in Einstein, you usually have a constant vector, and it makes sense conceptually that you would like to preserve the length of vectors when you transport from one place to another, because this allows you to make conclusion about what is happening at far places in the universe based on what you're measuring in your lab. But it doesn't have to be the case. And that's what is actually the Weyl integrable geometry. Original idea of the Weyl was saying, well, probably nature is such that I can choose any units I want, any place I want. And that's where Einstein objected, well, but then this would make total chaos of the information coming to us, because everything that we observe would depend on the path it arrived to us, and this would be very difficult to make any conclusions what we were really seeing there. The integrable Weyl geometry is saying, well, yeah, but let's just assume that you carry it, you don't preserve the length of the vector in any motion, but you preserve it if you carry it along the loop. So the result of this is that any information that comes to you from any other place is interfering in enforcing the same kind of data and conclusions that you get. Doesn't matter which part the information comes to you.
Whatever you said right now sounds very interesting. Unfortunately, I did not even get 5% of what you said. So,
Well, sorry about it. I was trying to keep it low.
DJ, would you be willing to give a talk or series of talk on this topic at the New York Quantum Theory group?
The quantum computing group?
No. There's another group, New York Quantum Theory.
Oh, okay.
New York Quantum Theory.
Mhm.
We have coordinated with Matthew. So Matthew's sessions are on Saturday. Our sessions are on Sundays.
Okay.
And for the next couple of sessions, we already have some scheduled talks about the black hole information paradox and potential
Mhm.
solutions to this paradox. But maybe after this, you could give us one or several talks about the stuff that you mentioned right now.
Well, okay, Matthew, can you drop me the link and I'll look at, basically, I will assume that you have already the schedule there from previous talks so that I will see whether I can bring up something that is lined up with what you're already having in your schedule.
Okay.
Yeah, I'll drop
As
you.
far as what we have on our schedule for Sundays, it is just for tomorrow and most likely a week from tomorrow, it is going to be the black hole information paradox.
Mhm.
And basically in that forum, we have different speakers. And usually we have one speaker, a different speaker every week or every other week or something like this. So it would be great if sometime in the near future you would be willing to give us one or a few presentations. It would be great. By the way, DJ, where do you teach?
Well, I'm distributed. My wave function is very spread these days.
Yeah.
I teach introduction to quantum computing to some students at New Bulgarian University in Europe, in Sofia, Bulgaria. And then Matthew is one of my mentee in the Quantum Open Source Foundation, where I'm working with a few people on different projects, and they're kind of international. Some people are from Colombia, some people are from Korea. So my wave function, when you start interacting, is really spreading out.
Okay.
But I'm located in California.
Okay. Just one last question. Based on your name, are you in any way related to Valery Gergiev?
I'm not sure who is Valery. Georgiev is very common name, family name in Bulgaria. And Valery is also a common name. So I don't know who is Valery Georgiev.
Gergiev, not Georgiev, Gergiev. He's the director of the Mariinsky Opera.
Oh, no, no, I don't think that we have relatives in the singing industry, in the music industry. We have very good friends that were actually performing, and they were involved with the San Francisco Opera, but not, I mean, like you said, Valery, I don't know it.
Okay, just because of the similarity of the name, that's all.
Yeah.
Maybe Marty knows that person.
No.
Marty's musical.
Yeah, I'm about to put up some of my saxophone playing online, so
Oh, okay.
give you the link.
Can you, maybe you can accompany that, or, one of our presentations can be accompanied
No,
by your
I can't.
saxophone playing.
I can't imagine what would go with quantum mechanics.
Something
Yeah.
weird.
Actually, for one of the talks, I was giving a talk about quantum music composer, but that was last year. I mean, it was 2019, before the pandemic even. But haven't worked on that. There's a kind of cool tool that one can build a music composition using a quantum computer.
Yeah, and actually, I saw there was like a some kind of residency or fellowship or something in the United Kingdom where they were trying to form a group to work on quantum music, or like, ways of kind of opening up quantum hardware in ways that like musicians, experimental or otherwise, could play around with and generate.
Hey, Matthew, that's right up your alley.
Yeah.
I thought about it.
Yeah.
I know one guy from the Qiskit community. He's actually a music professor in England, and he was turning into quantum and building things there. So maybe he's involved with that too.
And Einstein played the violin.
Yeah.
Wait, can I ask really quickly just about the scale invariant thing? Like, I just was curious, like, so the trick is that, like, if you go in a loop, the lengths aren't deformed. But if you just go from like A to B, something might end up a different length. Now, like, is that how you avoid? Because like I always thought that the problem with like scale invariant theories was that like that there's gonna have to be a fundamental length scale, like the Planck length or something. Insofar as, you try to, look at something really, really tiny, you send a really high energy photon to look at it, it collapses into a black hole. And so there's like going to be a sense in which, stuff is going to have to bottom out.
Yeah.
At some length.
But that's why we have the vacuum there, because it comes from the equations. When you write Einstein equation and you want to throw away matter, so the stress energy tensor is 0, then you have to see what is left. And if you're like this, then basically you're not left with much. I mean, because the Einstein equation would force the Ricci scalar to be 0, which would force then the Ricci tensor to be 0, and basically nothing would be left. But if you look at the extension to well integrable geometry, then what is left is right exactly this scaling factor. And you find equations for this scaling factor that have to be satisfied, which you can simplify it when you assume that the scaling factor would depend only on time, but not on location, because you want to have a homogeneous and isotropic universe.
So, by the way, conformal field theories are scale invariant.
Yeah.
Roger Penrose's conformal cyclic cosmology, if anyone's familiar with that, Roger Penrose, where where our universe transfers into the next Big Bang, so to speak.
Right. So that's right. But I was looking at his papers and I was surprised because I was always busy with other things, and for a new paper I had to look it up, and I noticed that basically he had only a few papers, and it was mostly philosophical argument rather than really computational thing behind, except for the thing with the cosmic microwave background, where there's not much really computational. They're just saying, well, if there's a black hole that evaporating in the previous eon, we should see it, and things like this. So I think what we have done with Professor Mader, we've done the computational part, not really being aware that this is part of the Penrose idea, because this is pretty much exactly the same conformal factor, but you make this conformal factor, you force it to be only time dependent, and then you define a cosmic time, because this way you avoid the problem of that space should be isotropic and homogeneous. But then it doesn't have to be time, because the time for us is difficult to look at different times. I mean, we can make conclusions, but it's not the same. And,
Well, of course,
yeah.
Of course, any measurement of space or time requires a material object to measure.
Right.
If you have empty space, you can't measure space or time.
Right. But that's why when there's a solution for the vacuum, when you insist that these equations are the scale variant, and you are actually assuming that when there could be a cosmological constant, like in Einstein cosmological constant, this cosmological constant is perfectly okay, but then it turned out that it would scale depending on actually what kind of scale of units you take, which would of course be related to the scale and the size of the universe. Naturally, it kind of brings it all together. But you can create units where your scale factor makes sense, so that at the Big Bang, when very, very far away, when you're kind of looking back in time, it really corresponds to solution with special scale factor 0. And then it expands to the current moment when the scale factor is 1. And the results are very encouraging, because we see that we can have actually the density fluctuations for the early universe to result in growth of structure formation, the matter, that what we see now, much faster than what is usually in theories. I mean, that's one place where dark matter is needed, so that you would push the structure formation much faster. But we found that we don't need really dark matter. We can put in if we insist, but if actually the model by itself shows that you can grow formation structure much faster, well, why do you need it? In a similar way, any lambda CDM parameter model could be found a nearby scale invariant vacuum model. I mean, it would have a little bit different parameters, but the evolution of the scale factor would be kind of very similar. So we are looking into things where we can actually try to differentiate them. I try to get some NSF proposals on this, doing on the microwave, because it takes, I mean, actually significant effort. So far we haven't had luck with getting funded on this, but hopefully at some point we'll see.
I heard right now a lot more than what I've been able to digest. So
Yeah.
I would like to hear it a lot more slowly so that I can follow you. But
Well,
right now I have to leave, because I'm really in a situation of circuit overload where
Yeah, we should probably call.
even if you
yeah,
talk
no,
very slowly, I will not be able to follow.
yeah. So Matthew would give me the link to your meetup online, so that I can check and see what are the things that, maybe I can join the meeting tomorrow if I have time. I don't know.
Yeah,
Depending on what time is the meeting.
Yeah, it is at 4 o'clock. Is it 4 o'clock tomorrow? And if you can join, this would be great.
But this is 4 o'clock Eastern time.
Yeah,
Which would be 1 o'clock my time, which is usually perfect. But then I'll have to see, because there was some discussions in the family to go something like hiking or something, and we will have to see.
No, that's not good. Hiking is not good.
No, hiking is very good. You can keep your social distancing, and you can get clear air.
I know.
Oh yeah, Jamie's just dropped the link to the meetup actually on the chat.
Yeah, thank you. Yeah.
Yeah.
Cool. Well, thanks everybody for.
Thank you, Matt. Really appreciate it as usual, and I'm looking forward to next week's meeting.
Yeah.
Yeah.
Thanks.
Okay, bye guys.
Thanks, everyone. Thanks, Matt.
Bye.
Bye-bye.
Bye, everyone.
Bye.